Okay, so is this 62? This is not. This is 63. This is part 63 of my PAINT5D sprint, which is not really much of a sprint anymore, is it? Yeah. We've been working on other things besides the camera, but the camera controls are still not finished. So, like, even though I'm kind of, like, wandering off into different areas, I want to make sure that I remind myself that the main thing I'm working on is the PAINT5D system, and there's other systems that are kind of like branching from that as I'm doing this. So let's go down here. So I was trying to create an image where I was going to like rotate an image in place, and I had some problems getting that to work properly. And now I realize that there's no real way to get a rotation in place with the way I've been doing it. Right, we can take anything in this bow tie. Let me think about this. Yeah, because now this is duplicated. This and this is now the same thing. Okay. Yeah, so I know how we can fix this. So right now, we have a section where we're saying, you know, if we're inside the bow tie, do all this logic and whatnot. I realize now that there's this kind of like, there's this cascade problem where if I rotate one pixel to another location, the pixel that was already there needs to be rotated to another location, and then that pixel needs to be rotated to another location. It cascades all the way around. And eventually what happens is one pixel ends up overlapping another pixel. So we need to keep like a queue of 4 pixel values in the four different rotational positions in order to fix this. So what I mean here is like, so let's look at this. We have an image here. So if we have pixel 1 here, and then we have pixel 2 here, and then we have pixel 4 here, and we have pixel 3 here, and we're trying to like rotate an image, right? We're trying to rotate this image. Okay, we're trying to rotate this image right here. And we're going to try to just, let's not worry about all the pixels, let's just worry about the pixels on the exact corners, right? I have to take this pixel and move it over to here. But if I don't back this pixel up, then I'm going to lose this pixel, right? So I have to take this pixel, move it over to here. I gotta take this pixel, move it over to here. I gotta take this pixel, move it over to here, and I gotta take this pixel and move it over to here. So what I need to do, in order to get that to work, is I need to back up this pixel, right? Back up 1. I need to back up number 1, and then I need to rotate 4 to here, then I need to rotate 3 over to here, then I need to rotate 2 to over to here, then I need to rotate 1 to over to here, and then after 1's been rotated, then I can use the backup. Sorry. Rotate 4 to over to 1, 3 over to 4, 2 gets rotated over to 3, and then 1 well, 1 wouldn't be rotated, right? We use the backup, right? So, because 1 is already overridden, right? So, when we rotate 4 over to 1, right, this is already used. Then we rotate 3 over to 4, that's already used. We rotate 2 over to 3, now that's overridden. We can't take this over to 2 now, because it's been overridden, so we gotta take this back up and put it over here, and now we can have successfully rotated everything. So we got to remember that as we're kind of trying to code this, right? So, before we were saying, you know, if I'm inside the bow tie, I was saying if I'm inside like this, so let's talk about what the bow tie is again, because I need a refresher myself. So let's do a 16 by 16 image here. We don't need too many pixels to draw this out. So we want to rotate this image. Remember how, in order to rotate this image, we got to be really careful about how we select the area to rotate. So the first thing we're going to do is just, let's turn anti-aliasing off, because I know it probably is on. So the first thing we got to do is we make a bow tie. So here's my bow tie. And I was saying, you know, if you're in this section, if you're in the bow tie section, then rotate, right? So I'll take this and move it over to here, take this and move it over to here, and we'll have no overlap if we do that, right? We gotta make sure that every single pixel is only rotated once if we're rotating in place. Otherwise, we're gonna have horrible problems, right? But this pattern, this red and orange over here, doesn't exactly rotate and fit into here because this red here overlaps, right? The red overlaps. So in order to do that, we do a x equals y line here, and we exclude this x equals y line. So now the bow tie is these red pixels and these orange pixels. And I was saying, okay, if you're inside this bow tie, then rotate. But now I'm saying that not only that, but you also have to be on you have to be on the left side as well. So let's use like a lime color. You got to be on the, not only that, but you have to be on this left lime side, right? So you have to be inside the bow tie, but only inside the bow tie on the left for this to work. So you got to be on this side, and you got to be within this orange. You got to be within the orange or the red. And if you're inside those pixels, then we can do the rotation algorithm, right? So, right. So that idea of what we drew out over here or over here, right? We're going to take where we got this red pixel down here, right? This pixel 4, and we're going to rotate it over to here. And then we're going to take this and rotate over there, rotate, right? It's all going to start from here. So let's save this as something. I'm going to put it into the doc folder. Okay, so we're going to save this as part of the documentation because this diagram is kind of important to understand how we're going to actually rotate this nonsense. Okay, so the current algorithm already has figured out what this bow tie is, but we just need to take the left side. So you have to take everything where the x is negative. With the way the algorithm works so far, I believe. So if we look over here, we see right, not on the diagonal, inside the bow tie. And then so integer x pixel width is going to be less than or equal to pix width divided by 2 minus 1, I think. Let's just put that somewhere else. Let's put that in a calculation here. Update. Only on left bow of bow tie. I'm going to make a note here to update, and so C doc/img/bowtie.png, right? So, and then we can also make a note of what video this was, so we can kind of find that later, right? So at vid 0, 1, 3, 1. And the time is 0, 0, 10, 10, 10. Right? And let's actually show that really quick, right? So when I'm talking about that bow tie pattern, if we go into the documentation, right, doc, and we go into image, this is the bow tie that I'm talking about. Can't really zoom in very... God, this... Gotta open it with paint.net to actually see the diagram, which kind of sucks. But, yeah, so if we look at this kind of diagram here in the doc/image/bowtie.png, this is what we're talking about over here. I'm going to change the timestamp so that we don't have as much delay. So let's call this 11:00. Let's call it 11 even. But yeah, so this diagram, what we're talking about when we talk about this diagram is actually over here on this side. So this right here is talking about this diagram here, right? So this is bowtie.png, doc/bowtie.png. And we only want to rotate things that are on the left half within this orange section, the orange and the red, but not on this x equals y line. So when we're looking at the algorithm here, this is the x equals y line, so this is a black line right here. And then this calculation here is making sure the magnitude on the x is greater than the magnitude on the y, which makes sure that we're in this bow tie cone on the right and left, right? And now we need a calculation to make sure we're only on the left side. So that's the thing we're going to do next. So let's kind of figure that out. So let's make a int32 left max index. Left max index equals the pix width divided by 2 and then -1. So if we had a 4x4 image, then the maximum left index would be 1, right? Because 4x4 divided by 2, we get 2, right? Just 2 pixels, and those pixels are addressed as 0 and 1, right? So this right here max left max index forward. We're kind of out of room here, so let's just... Okay, max left index, right? So this thing right here. So with that, we can go over here, and we can say IX needs to be less than or equal to this left max index, right? Left bow of bow tie, right? So this is the left bow of the bow tie, is what this is. And then down here, where we have all these decisions, are we in left bow of bow tie? Right? And this isn't really left bow of bow tie, right? That's what we're trying to calculate here, but this is just left half of image, right? It's the left half of the image, right? So, so all of these things will get us the left bow of the bow tie, but only pixels that are not going to be repeated if we rotate, 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 right? So the reason why I can't have this black is because if we take the black and the red over here and we try to rotate it, then we're going to get overlapping pixels every time we rotate 90 degrees, and that's not going to work for our rotation algorithm. So now that we have that, let's just close this. I don't think I actually made any changes. Don't save. Okay. So now that we have that, I know we did like a lot of stuff where we kind of fixed your bow tie filter. So this probably can be nuked. We can probably nuke this. We were taking shots in the dark yesterday. Now we have this temporary backup, right? Temporary backup. We're not using it anywhere yet. And what we're going to expect is we're going to expect the... so D2, NX. NX is the new X. Okay. So let's just take this and see what the result is. And we're going to see most stuff is going to be blacked out, but hopefully we're going to see some of the image rotated. So let's take that for a spin and see if we... if our algorithm kind of does what we think it does, and then we can fix it up. We can fix it up once we have... Once everything looks proper from this point, we can fix it up a little bit better, but we got to start from here. Okay, so let's press P key. Okay. And now let's go O for output. Let's close this now. And let's go into the mod folder and open up PAINT5D and kind of look at what got saved. And well, okay, so we can see that it was able to take, it took this image here and it moved it over here, right? So that's a good sign. It only looked at this and then it moved it over here, right? That's all that's happening here. And we can see that it's a duplicated section. That's why, even though we rotate it in place, we're still getting the same image over and over again, because this quadrant, I don't know if you want to call it a quadrant because it's like a diagonal, but this diagonal slice here, this diagonal quad and this diagonal quad, this pie quad, I don't know what we want to call it, pizza quad? It's like a pizza slice? I don't know. Pizza quad. This left try and this top try are identical, so when we try to apply the rotational algorithm over and over again, we don't see any weird compounding effects, but it's still, this is close to what we need to do, right? So the algorithm is rotating right 90 degrees, so that's good. And so we know that we're starting at this bow tie, and then the new position is over here, right? And so we need to do some math on here so that we can keep track of the different quadrants, right? So we need to, if we look at here, so RX, this RX is pretty good, I think. But we're going to have to, make an array of locations. So over here, let's do like int32, and we're gonna call this so we're going to close this off a bit for a second. So I know exactly what needs to be done, so it's not, this isn't too bad. But, right here, actually here, let's put this over here for a second. So right here, we're going to have to create an array of int32s. And it's going to have to be, it's like a pie slice. I don't know what to call it. 1, 2, 3, 4. Okay. Pi slice pixel X. And this can be pi slice pixel Y. And what we can do for the pi slices is we have this kind of thing going on. Let's actually try to just redraw this, maybe. Try to get some better diagonals going on here. Because those diagonals just kind of suck, don't they? And I think it's because my ASCII... Drawing ASCII doesn't really give me perfect 45-degree angle lines, I believe, is what the problem is here. But let's see if we can just try to draw something a little bit better. Like this. Oh, that's a little bit better. And then we'll have to go like this. Okay. And then... Okay. I'll take all this. Just take all of it and try to rotate it. Yeah, there we go. And... So this isn't the square... This isn't a perfectly square image here, but it's squarer than what I had before. So because of the way I do comments, we're gonna have to color code this somehow. Okay. So this will be 1, 2, 3, and 4. Oh, these are just locations, right? So okay. Okay, you know what? Let's not complicate this. Original red, original green, original blue, original alpha. Right. These are going to be the original colors. And then we want to keep track of these different locations, right? We're going to take we're going to start off with only a pixel that is in this 0 location. And then we're going to rotate 90 to get a location somewhere here, rotate another 90 to get a location here, rotate another 90 to get a location here, right? And yeah, I mean, alternatively, what we could do is we could do 1, 2, 3, 4, and then after we rotate for the 5th time, we should end up back here, right? Or something like that, right? So maybe we want like a 5 in here. I don't know. I have to think about what makes the most sense, or what is going to be the easiest to do. Also, I need to take a... I know I just started, but I need to take a quick break. So, yeah. Yeah, so let's, oh, original. Original red. Original green. Original blue. Original alpha. Red, green, blue, and alpha, right? Original red, green, blue, and alpha. Now, possibly to make this easier to see, maybe making these capital letters, just so that the prefix is less visible. But then we gotta be like, well, if that's what we want to do here, then do we want to do like, make this a PX, PY, just to be consistent, right? So, like @vid IID. And the time is 27:33. And this commentary kind of applies to here, right? So I went a little bit overkill there, but let's call it 29. Let's call it 29. Or 20, 28. Yeah, let's just call it 29 for a second. This might take me a while to cut and paste this everywhere it needs to go. Or 29. Yeah, 29. Let's just call it 29. Okay. And it's video 131. So we're going to explain it one more time for the camera, for what's going on here, when it hits 29. Just to make sure that we can, just so that if somebody's scrolling through the video archives, they don't have to, like, scroll back and forth and whatnot through this and all that stuff. So, 55, so we're about to explain this stuff right here. And 29. So, this diagram right here is getting a pixel from this pie slice, this pie slice, this pie slice, and this pie slice. Inside this number 1 section, that is the left bow tie we're talking about. So when we go down into the code over here, these if conditions are getting us into the left bow tie, right? So if we see down here, are we in the left bow tie? So here's where this conditional ends, and here's where the left bow tie prediction kind of starts right here. So between these two cyan regions of code is where we're going to get into this bow tie, left bow tie section right here that's labeled 1 here, okay? Once we do that, we want to rotate this 90 degrees to get over here, rotate another 90 degrees to get over here, rotate another 90 degrees to get over here, and get all these different pixel coordinates. And then we're going to store those pixel coordinates in here. I don't know if I want an extra coordinate or not, but we need at least 4 pixel coordinates here, right? The original, and then the other ones. And the reason I was thinking 5 elements is because then I could label this 1, 2, 3, and 4, and that might make things easier, so do that. Now we should probably make everything line up in parallel, so do something like that. And so these colors right here are going to be the original color pixel that was here, the original color pixel that was here, the original color pixel that was here, and the original color pixel that was here. Okay? And once we know what the original colors were in these different locations, and we know what all the transformed positions are, then we'll be able to perform a rotation on all 4 of those pixels to effectively do the 90-degree rotation of the image on just 4 pixels, right? And so we'll keep on going through the entire image 4 pixels at a time until the entire image is rotated. And that's why we're only going to look at this 1/4 pie slice as we're looping through it, because since every time we pick a pixel out of this 1/4 pie slice, we're going to take 1, 2, 3, 4 pixels, right? So 4 times 4 gets all the pie slices, and it gets all the pixels, right? So if we iterate through every single pixel in this slice, and then we rotate 4 pixels, well, every single pixel here, multiplied by 4, is all of the pixels in the image, if that makes sense. So I need to take a quick break, but I just wanted to describe that before I went on a break, and we'll try to figure out this once we get back. So, and maybe I'll do some more push-ups as well before I get back. Try to get these out of the way. So... So obviously not back in time, but okay. So while in the shower, I had an idea, and I think a lot of good ideas just happen in the shower. So we're gonna draw that out really quick before we. I want to codify that idea I had in the shower. Because I think the math works out nicely. So I'm thinking, hey, how do I get a whole bunch of like hard-coded assets for tile designs into the engine, like the next layer of abstraction removed from the PAINT5D system, right? So to make these fractal auto tiles, it's going to take a lot of different systems, right? So the PAINT5D system does not create fractal auto tiles. It creates the base materials or the base auto tiles for the fractal auto tiling. So let's do a new layout, a new 512 by 512 image. And we're going to keep all of our data is always going to be 512 by 512, right? And that's going to make things easy to work with here. So I'm thinking that on a 64 by 64 pixel canvas, that I also need a 16 by 16 as well for a second. So 16 by 16. Okay. So let's get out our brush, or whatever the heck we got here. And okay. Copy that. And is this our... This is our 64 by 64? Okay. So if we take away 16 by 16 and we take away 16 by 16 here, we've taken away 32 by 32. Okay. So my thought is that... Here, let's try to change the color over here again. Change this to red or something. Paste this over here. I'm getting to something, I swear. So I was thinking about memory locality as well as the ease of creating source graphics. So even though we're going to create editors to make this process easy, I want something that... I want a layout that's relatively sane for being able to... create images. Let's flip these pixels. Image... Invert colors. Okay, so let's say I'm going to invert all the colors really quick because technically black is nothingness. So anti-aliasing, gotta turn that off. Wrong size. Paint.net isn't the nicest editor for like just pixel-based art. In fact, it's horrible. Okay. So let's say we got something like this. And what I'm thinking is, you could have... That's not exactly what I wanted to do, is it? 1, 2, 3, 4, 5, 6, 7, 8. Well, this is 64 by 64. We got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's not really what I want, is it? So what is this? This is 32 by 32? Sorry. Okay. So 64 by 64. I swear I'm going to explain this once I actually have it all drawn out. Okay, well that's a little bit bigger than I was anticipating, but okay. So that would mean we need 32 by 32. So 64 and 64, 128 and 128. Hold on. What do we got here? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We got 12 images here. Well, let's take this and roll with it for a second. Because it might be interesting to just see how these fit into each other. So I want to think about how we can pack data in a way where there's a little bit more locality compared to the way we did it before. So I'm going to take some time to... I know I was in the middle of doing, like, rotating pixels and whatnot. But, you know, you don't always get interesting ideas all the time. The raw algorithmic goodness, that's just a time sink. But as far as, like, oh my god, I have this great idea. You don't really control when those happen, right? So, if we got an idea, and we want to think about, if we want to extrapolate it, then we might as well take some time to do it, and see what we're thinking here. So I was thinking we could have, like, the big squares you're seeing could be a design, and those designs themselves could be painted using the smaller, the designs in the smaller squares. So designs in the smaller squares are used to paint designs inside here, if that makes sense. That probably doesn't make perfect sense. I'm just going to keep on going, and... Now, the problem with this is that there's 12 subsquares around the big square, and the PAINT5D system creates 16 tile sets. So what I was thinking is that these little squares could be little designs, and those designs could be, they could be like a monochrome design that's done with one of the materials from the PAINT5D system. And then what we could do in here is we could put something bigger, right? So let's take that, and let's take this for a second, and so this was... Okay. So this thing right here is 64 by 64. So the idea I had in the shower, I thought I got the numbers wrong by 1 power of 2. And so I want to fix that while I'm here. Oh, come on. Well, I have the idea. So this is a 32 by 32. So we need a 128 by 128. File, new. Okay, so we're gonna put these... Well, I see, anytime we do that, we're still gonna get that problem, aren't we? So... Let's go with 8 by 8. So I want to figure out a way to make making graphics for this engine kind of like interesting and fun. 8 by 8, I don't know. That doesn't seem like enough. That doesn't seem like enough pixels to get something interesting, like an interesting pattern, right? There's not very many interesting patterns you can make with 8 by 8, right? So 8 by 8, too small. Now I think that 16 by 16 though was enough, where I think 16 by 16 was just enough where it's just enough to where we can actually start to draw things that are visually interesting, I think, where we can get some kind of visually interesting patterns, if I remember correctly, where we can kind of start to do things that are, it's not we can't get too much detail, but we can get enough detail to start making things that I would call interesting, I think. And also, if we only focus on one corner, then things also get a little bit more interesting. However, focusing on one corner kind of makes the data kind of look confusing. But I do like the idea of like data leverage. So if we have an image like this, and we want to create like a canvas where we have a whole bunch of these around a bigger image, want a whole bunch of these around a bigger image. Oh, let's make this red or something. If we want to have like 16, we're gonna have like 4 of these things. So I just want to see how the math needs to work out for for the idea that I'm kind of thinking. So I want like 4 of these, and then we have something on the corner. Oh, Control Z. We have something on the corner. So that is 16, 16, right? 32, 64. So it makes a... the level design that I actually want, I want 64 by 64. So that could actually be interesting to where... for each level design, we could have... we could potentially have our own texture set for every single level. That would actually be kind of cool. What's the canvas size here? 128 by 128. So doing this is not... Right, so this is a... I see. Okay. I'm going to try to move this over. Maybe not like that. So I know that what I'm kind of thinking isn't very, I'm not describing what I'm thinking very well right now. Okay, let's take this and let's just nuke out these pixels for a second. Control A, Control Copy. Rotate 180. Okay, let's go back here. I guess we'll need a new layer. God, just... I need a better paint program, like something that's more like MS Paint, if anyone has any suggestions. So 16, 16, 32, and 32, right? So that gives us... This is our 64 by 64. So, hold on, let's just get something that's... Let's go find a 60... Not a 64 by 64. Let's close this. Let's close this. Okay. File, new. Let's get something 64 by 64. So 64 by 64 is the size that I want levels to be. And let's, just color this green or something. So that would be, yeah, it's somewhere in here like that, if that's how we're gonna roll. So if we're really careful, we can get this nicely aligned. And if we're not careful, it's gonna be off by 1. Okay, that looks like it's centered. We're gonna make absolutely sure it's centered. But I was thinking, oh, wouldn't it be nice if, you know, these things that are red are like the 16 base materials, right? And then you can kind of paint things in here, right? So these are like images drawn with the base materials. And then the base materials can be rendered slightly differently depending on what level you're in, right? However, we have all this extra space. Let's merge this down. That's what's going on here. So I'm going to take these different partition ideas, and I'm just going to keep them around, I guess. So this is a 32 by 32. And let's just give it a different color. How about configuration data is cyan? C for cyan or configuration. And actually, let's put like a darker cyan around it. Or this isn't really a dark cyan, it's more like a... Here, let's make that a little bit more cyanish. Okay, there. Let's put like a little dark cyan around this. Okay, let's go back over here, and let's kind of paste that in these different sections here. So what I'm thinking is that within the level data, you can encode some metadata in these cyan sections, these configuration sections. And then these red sections you could use to encode some type of tile designs. The problem is that this doesn't work out as nicely as I thought it was going to. Let's get our tools here. Let's swap that. Okay. We'll just color code everything. Okay, now we can give it a dark red. So we're thinking, hey, tile designs could go here. You could have 16 different things for tile designs and then 16 things for the bomb designs, maybe, right? That could be a thing. That could be how that works. And then configuration, right? So then over here, let's give this a little border. And then let's kind of say, let's make a note here, right? So let's actually write on here and say, 64 by 64 level. Right, so this could be a 64 by 64 level. Right in here. And then, what this could be up here is we could have 16 tiles. And then we could also have, over here, we could have 16 bombs. just going to say bomb instead of bombs, just because I'm running out of room, right? And then over here, let's use black. In these sections here, it could be CFG configuration, right? And then same thing with over here, right? This could also be CFG. And then let's just copy paste. So this could be CFG, and this could be CFG, right? So let's save this in our notes. So let's go into documentation images, level data idea. Is this a level data idea? Where how we could partition things on a 512 by 512 to create kind of like this, this kind of level kind of thing. Now, I think I'm kind of wrong here. Canvas size for a second. 128 by 128. So there would be 4 of these levels. If we packed it like this, we'd have 4 levels on a single texture. If we did that, right? So this is just an idea. This is not how I'm saying I want to do things per se. But let's come back to this idea over here, where we have kind of like the image of this size, and we don't exactly have so how big is this? This is 64 by 64. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, well that's 64 by 64. The next thing we would need was 128 by 128, the next power of 2 up. And this is already 128 by 128, right? Yeah, that's 128 by 128. I'm gonna copy this for a second. Paste that. So the idea was like, hey, we have this nice little design, and then we have other patterns over here. I mean, we could still do something like that, right? It's just that the palette would have to be, for this design, we could do 1, 2, 3, 4, 5, 6, 7, 8 colors. Use these for some type of configuration. And then the 8 colors could be 8 colors selected from the base materials. And there's 16 base materials, right? So that could still work. It's just not exactly how I was envisioning things. Let's take this for a second and let's adjustments, hue saturation. And let's make this intersection a little bit darker. And then if we could get it to be... No, let's not change the color like that. Let's keep the color tuning. Color tuning, we're not going to change the color tuning. We're just going to make it a little bit darker. Okay. And then we're going to take this and close this. Don't save. Don't save. So if we're looking at a 512 by 512, so how many of these, if we think we want to do stuff in that kind of a manner, how many of these are we going to end up with, right? I think we end up with quite a lot. How does that fit into everything else we're doing? Like all the bits and everything needs to, all the math needs to work out nicely when we're doing this. So we got 1, 2, 3, 4, 5, 6, 7, 8. We got 8 things. 8 by 8, that's 64, right? So that is a big hefty chunk of stuff here. Copy. And then 64 materials could be a lot of things to select from, I think. I think it's more than enough. Right, where we do something like this. And each one of these materials, this graphic will be drawn with these graphics around here. And then these corners can be used to store configuration information. Like, for example, these corners can be used to store configuration information. For example, the palette used for what materials these select from. And then when we draw a pattern in here, that pattern will be drawn using these tiles, right? That could be, I think that could be interesting. Okay. So 64 is quite a bit of things here, right? 64 is a lot of materials. Now, however, 64 is what? 1, 2, 3, 4. We could say we have 16 of one category, 16 of another category, 16 of another category, 16 of another category, right? We could have 16, because we don't just need tiles, right? So 16 different types of tiles seems like enough to where we could get enough interesting stuff. So like 16 types of tiles, 16 types of bombs, and then 16 and 16 of something else that I don't know what it would be yet, right? Like little flare details, maybe the I don't know. But let's just say so 6 times 6 is 64? No. Yeah, right? Yeah. No, 6 times 6 is 36. 8 times 8 is 64. You know, you'd think that, you know, the calculator works until you do something like that. 8 times 8. 64, yeah, 64. So, 64 vid IID 0 0 1 3 1, and time is 1 31 let's say 13 31 13 dot PNG. That is a kind of long name. But that's kind of the idea I had in the shower. So let's kind of close this. I'm not sure I like this idea. Well, let's look at this for a second. So if we did something like this, yeah, not a fan of this idea. Knowing where this is going, though, let's just say, let's save this as so 131, and the time is 1 hour, 32 minutes, and 3 seconds. .png. Okay, we're just gonna call that unfinished thought. Okay, so let's close these. Close that. Don't save. Okay. So let's open that up really quick. Make sure that in our documentation we have that. So we have images in the documentation, and we've tagged them with the video number. So we have this kind of idea for creating materials, and we're thinking we could subsect these into, you know, 16 different materials for drawing the level, 16 different materials for drawing different kinds of explosives, like different types of bomb sprites, and then 16 different something or other, 16 different something or other that we don't know what they are yet, right? Or we just say it's a reserve, we don't know what it's used for yet. Eventually we'll use it for something, right? Something like that. So that's an idea. We could also say that, what we could do is we could say that, you know, we could use 16 graphics, and then these could be lighting adjustments, like lights. So this could be the solid part of the tile, this could be lighting information, right? And this could be the bombs, 16 different bombs, and the lighting information for those bombs, you know, something like that. Or some type of something, I don't know. So actually, let's open that up one more time, make sure everything's here. So that was that idea. There's that bow tie from the diagram. Another partition idea, right, where we have a 64 by 64 level, and we hard code the different materials designs into the actual image, like that. Like, that's an idea. This is an unfinished idea where, you know, we have something in this white area, I don't know what, and then we have all this data here like that. So different ways to think of how we could partition data when we get to the next level of abstraction. But yeah, let's finish up the rotation algorithm. So the rotation algorithm for this, let's go in here and kind of figure that out again. So we got the pie slice pixels and whatnot. We got these backups, the original colors, and there are let's just zero these out. I mean, I guess you could put a hex value there, right? It'll be using a single element only works if you supply 0. That does not actually work if you supply anything else, so it's kind of misleading. But the idea is I just want to note that, hey, this value is supposed to be a byte value, and these values are supposed to be integer values, so that's why I notated it that way. Okay. So then, over here we have, like, rotating stuff. And I'm thinking in here we create, we do another loop and we create, figure out all pixel locations. Okay, figure out all pixel locations, right? So we're gonna say that, so well, let's just do this first and then think about. Okay. So let's do 1 to 4 here for a second. 1 to 4. And this fx, fy is... oh, that's a float 32. Okay, so all of our locations are using float. And I see why that is. Because the way we did our rotation algorithm around the center. Well, if that's the way we did it, that's fine. But that means that we have to change this to float 32. And let's notate it as 0.0, I guess. That's fine if that's how it works. Rx. And it's actually fx, fx, and fy. And then put this up here. So this is the rotation algorithm to rotate, and then this is just the math to get it back into the pixel coordinate, right? So this is just transforming. This is transforming the coordinate space here, but this is the actual rotation. Now when we rotate, we gotta take the, to get the rotated x, we have to minus the y. And to get the rotated y, we just use the x. Right, so this is the formula. So we swap x and y. Well, x and y get swapped. Rotate by swapping x and y. And inverting only right? So that's what's going on here. And we're gonna seed, right? We're gonna seed px and py with this the 0th, right? The fx and fy, which is this is the fragment chord. And so we go all the way up to 4, right? Because it's 0 to 4 for 5 things. I'm doing 1 to 4 here. Okay, that's fine. So that means the 0th section here, if we want to write it that way, then that means that this is still this, right? This is this. And this is actually 0 or 5 over here, right? This is 0 or 5, because it goes 0, 1, 2, 3. Did I say 5? Sorry, 4. So 0, 1, 2, 3, and 4, right? So if we go 1, 2, 3, 4, or we can go 0, 1, 2, 3, right? So the 0th and the 4th should be exactly the same. Like if we rotated, and rotated, then the 0th and the 4th should be exactly the same. And we could use that as a little check to help us make sure that this math is actually correct, right? So we could say, you know, if px 0 not equal to px 4, 0, 1, 2, 3, 0, 1, 0, 1, 2, 3, 4. Yeah. If that's not equal, or py 0, or not py 0, but py 4, it's not equal to py 0 not equal to py 4, right? If any of these cases are not the case, then the rotation, our rotation algorithm didn't work, right? So error, your rotation algorithm sucks. 2021. That is my election slogan. Okay. So we want to figure out all our pixel locations. Rotate into 4 pi slices. Right, so we're rotating to 4 pi slices. That's a better description as to what is going on in this section here. And we could really kind of do that if we wanted to, right? We could indent that like that. Then we can shorten up this message so we don't go over our column boundary. And then we could do more, but let's just see if this code compiles and see if this assert does not get triggered and all that good stuff. And if it actually compiles, then we can kind of keep on working this into the code. But let's just take it one little step at a time here to get this working. So when I wrote this, I was semicolon happy. Alright, so to rotate this, to get the rotated whatever the heck here, we're going to take the previous thing, right? Yeah, we're going to take the previous thing. And the rotation is compound, right? So take the previous value and rotate it, then loop through here again take that previous value, rotate that, and it's going to compound on itself, is the hope. And if it doesn't compound on itself, then our then our whole algorithm for how to rotate is just completely wrong. So, missing this function, so we got to go up here for a second and define what air is. So let's go define Alright, so we'll make an error message. And we also have to go down to the bottom of the section and undef that. So, bottom of this section, we gotta go undef ERR. Okay. And now we can give that another shot. So the idea is that we're not going to change any of the behavior, but we're going to hope that the code that we've added, unused variable, yeah, so I guess we're going to have to, we can either write some no-ops to get this working, or we can start to add the other code that we're going to need, right? I think it would be easier just to write the code that we're going to need, so So let's add this stuff to an array eventually. So let's, so Rx and Nx, let's just go up here and say, you know, I don't know if these are the correct types. I think they're int32s. No, the NX is an int32, but the R is a float 32. We're going to declare them here, because we're gonna we just want to get this stuff working. In order to just get this working, we're going to within here to get those original colors. We can say that, you know, RX equals, you know, PX I, and then actually no, we want the original colors for each bow tie, so 0 to whatever. So let's do I minus 1. Yeah, so RX and RY. Technically, this is not the rotated value, but let's not worry about that. Let's not worry about that aspect yet. So we just want to get the so I just want to cache the original colors here. So NX and NY can be used to we gotta do index to XY though. So D2 is here, okay. So let's do that as well. D2. Right, so we want the component index of the pixel. That's what this is all about, this D2 here. And what type are those? Those are int32s. So let's declare those as well. So up here, we'll just say int32 D1 and Int32 D2. Component index number 1. They're just component indexes. Component index number 2, right? So they're very vague names. That's intentional. And then D2, we can calculate it like this. And then D2, after it's calculated, we can use it to get the backed up color, right? We have this backup color variable. That's the whole idea of why we did that. But now we can back up a series of colors, right? We want to cache the original colors. So we have original red, green, and blue, right? Original red, green, and blue. Original red, original green, original blue, original alpha. With the current index. Let's just do, call this I. Or not. I'm gonna call it I1. M1. Call it M1. And then here I'm gonna say, I'm just gonna define M1 as, you know, I minus 1. Then undef it here, just so that I can use it in here like this. Instead of I minus 1 everywhere here, I can go... Right, so I know that this x, this xy here for pixel x, pixel y is directly corresponding to these colors, because I can see them all light up the same color, right? Now... Yeah, sure, let's just call it M1. Could also call it loc for location, right? Because maybe later we won't want this to be a minus 1. Later we might not want this to be a minus 1. Later we might not want this to be a minus 1. Let's just call it loc for location. And then D2 is calculated here. We go into that pixel array, and we get the original red, green, blue. So caching. So cache RGBA for one of our 4 pixels. RGBA for one of our 4 pixels. That's what we're caching that, right? Okay, so we're still not going to use anything in here, right? But we've already hit all the locations and backed everything up. So what we could do is we could have a, in this loop, what we could do is, this assignment here, the first loop could be backing everything up, and then the next loop we could just, do the actual assignments, right? Because when we seed this, when we seed it, we'd have to have another outer loop out here, right? Because we seed it. And then we could just recalculate everything over again, and this time do the actual math of reassigning these values and rotating it. That might be the easiest way. Let's just see if we can get this compiling. Now that we're technically we're using all the variables, right? I mean, the compiler still might complain. Expected something something. So we almost did this correctly, but we still have to do that, right? Okay. Set but not used, which is true. It's set. It's set, but it's not used anywhere. So this just might be one of those things we're just gonna have to go in for the kill, huh? So what we can do here is we can say for int32 rock is going to stand for rotate or collect. Next rock. Actually, that's not right. Collect or collect or override. So CO. Let's use CO. Right. And we'll loop through it exactly the same twice, right? So px0 equals the fx and the fy. The fx and the fy is here. It's not done anywhere else. And then what we can do is we go through all this stuff. And here's our cache original colors. And right here is where we're caching it, right? And here's the location. Here are the, yeah, so what about the last loop, though? So is this a rotated location? This is the rotated location, huh? Not sure how I'm gonna do this. Yeah, but these locations are rotated. And so we're going through 1 through 4. So this location goes to 0 to 3. So it goes 0, 1, 2, 3. So it really makes sense if we sampled from here, 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 and here, right? So here we're applying some rotations. I starts here. This starts at I minus 1. Okay, so this is not rotated. This is the same. Yes, this is the original location, right? Because this is I minus 1. I minus 1 was never rotated. I minus 1 is right here. This is I minus 1, because 0 and this starts at 1, right? Okay. That makes sense. Okay, cool. So these locations are the original locations, and we're backing them up. And when we go through here, we also want to make sure, absolutely sure, that this cell and this cell are the same, 0 and 4. So 0 and 4 should be exactly the same. Okay, so that makes sense. That makes sense. So what we want to do is say, okay. So the first thing we want to do is case 1, we're going to do this. Case 2, we're going to do this. Default is going to be default, we just selected, default, you just somehow selected something that was completely invalid, right? So, default is this. Okay, so the first time we go through here, we're going to back everything up. And the next time we go through here, we're going to do our rotation, right? So, in order to do the rotation, we want the next, right? So let's define next, right? So we have, it's just I, right? So I is always in range, right? 1 to 4. So 0, 1, 2, 3, and 4. So we have the location, and then we have the next location, right? So we have the original location, then we have the next location. That's what a loc and next are going to be here. And right here, we're just going to say, we're going to have to flip this expression around a bit. And we want to say, we want to take the exact same well, D2 is, oh, I see. Well, let's solve it one step at a time here. So we know we need something like this. We say we can go through the exact same colors, but we can just grab from the color from the other location, right? So we don't have to change the coordinates we look at, right? We don't have to change the coordinates we look at. We can just change the colors that we're loading, right? And that will effectively create a rotation of those values, right? I think that makes sense. Could be wrong here. Now the other question is, are all these values filled out, right? Because when we're backing things up, we back up I minus 1. And do we get the last one, though, right? So I minus 1, we get 0. We get 0, 1, 2, and 3. But we don't get that, we don't get the fourth. Next. So we're going to store the location colors for 0. Zero, 1, 2, and 3. But the fourth doesn't get set. So this next thing, how it's one above this thing. The fourth is not getting set. The fourth should be the same as the 0th, though. So if that's the case, the fourth should be the same as the 0th, and the 0th is the only one getting set. So in order to do that, we can just do next modulus 4, right? Right, so right, next modulus 4, so 0, 1, 2, and 3, right? 0, 1, and 2, and 3, because this thing here is going to be 0, 1, 2, and 3 because of the minus, right? Okay. So I think that's about correct. But that does mean that we need to... this stuff, let's just trash this. Let's trash this. And then we're also going to be pretty confident that we have this correct, because now we did all the logic, right? So we actually have to comment out all this junk. And then we might end up with problems because this temp variable... Well, let's just see if we can get this compiling. And our case statement, we don't use case statements very much, but this case, and then default. So right here, this is a colon that needs to be a semicolon. Missed that. Okay, let's give that a shot. Unused variable D1. So D1 was kind of used over here to figure out the... Right, because we were going to try the index of the original location. We wanted to sample 2 pixel... We were sampling 2 pixel locations over here, originally. But then we decided, okay, instead of sampling 2 different pixel locations and trying to swap, we need to build a queue of like all of the different colors and then just go through all of the same locations twice, but then swap what colors we're using. Let's just get rid of the D1 here. Okay. So we'll see if this works or if it does something horrible. So let's go over here. Let's go P for pattern. Let's go O for output. So it didn't crash on us, so that assert must have worked. And then let's look at the mod folder and see if we have the correct rotations or if we have to fix something. So we're close. In fact, I thought this might happen. So we're rotating the opposite direction, right? So we're going 90 degrees to the 90 degrees counterclockwise. Another 90 degrees counterclockwise. So we can look at where the mouth is. The mouth is on the bottom. Now the mouth is over to the right. Now the mouth is over to the top. Now the mouth is over to the left, right? So we're close. And to fix that, that's not too hard, right? Because I kind of knew that our coordinate... I wasn't certain about the math for the calculations for rotation, because depending on if we got it wrong, we would rotate in the wrong direction. So... if rotating in wrong direction, swap the signs in formula. Right? So, as far as I'm concerned, all we gotta do is do this. And that's because... simple mistake, right? I never was very clear. I never had a good mental grasp on which one of these would be correct, just because we have kind of a different coordinate system. We're working with slightly different coordinate systems, right? So I originally did the math with the bottom left coordinate system, but the images have a top left origin, right? So I did the math with the bottom right origin originally. I did my calculations with a bottom right origin, but the math is applying to a graphic that has a top left origin. So in order to fix this, I'm pretty sure we just gotta swap this around, and now the rotation will rotate the other way, and then the algorithm will just work properly. So that's what we're hoping. We're hoping that all we gotta do is swap those signs, and we're good to go, and everything just works, and it's awesome, right? Or it could blow up horribly in our face, and we wonder how just changing the sign leads to some type of catastrophic problem. But let's just cross our fingers and hope this works. So we're going to hit P, then we're going to hit O for output, and then we're going to go into the mod folder and we're going to take another look at this, right? So we're trying to rotate clockwise. So now here, this gets rotated clockwise, and then the mouth is over here. Now the mouth is going to be on the top, and now the mouth is going to be over here, right? So the idea for why we're doing this is if we want... this needs to reflect an auto tile set, right? So this chunk of graphics on the top left is our top left corner. This is our top right corner. This is our bottom right corner. This is our bottom left corner. So if we want this to... we're trying to procedurally generate a tile set, then we would need to do these transformations properly in order to get that to work, if that makes sense. So yeah, we've got the rotation correct. We don't really have that... the results of this weren't that interesting in terms of what we ended up with. But now we have it, so that's cool. So our rotation in place looks like it's pixel perfect because the image doesn't get corrupted as we subsequently rotate it multiple times. So that's fine. There we go. We got a thing. Let's go clean up that rotation algorithm, though, because now we can we can just delete all this, right? We can delete all this. And then, instead of calling this D2 or whatever, component index of pixel, we can just call this com, right? We can just call it comdex, or com. So anywhere where we see this, we could just replace it with com, right? So int32, this is the component index of the pixel, right? So anywhere we see D2, we can just go com. Okay. What else can we fix here? We can make a note of this at least, right? This is center X, and this is center Y. Okay. Now, RX and RY do we need those anymore? RX originally meant rotated X. And this is a collection of rotated values, so I mean that still kind of makes sense. NX stands for new X. Okay. Rotated X. Rotated Y. New X. Rotated X as proper integer chord. So, right, because new X has to be, new X is put into is retranslated back into the original coordinate space, right? So that's fine. That's fine if that's how we want to write that. Okay, so we've documented all the variables, I think. The code works. I'm surprised that it works. So let's just give it another run, make sure it works. And then we got to think about what we want to do next, if we even want to do anything next, or if we just want to do some push-ups and save this for later. Okay, so closing that. We have this open way too many times. I'm keeping this one out for reference, but okay, if we open up this now, everything still looks good. My monitor's kind of dirty, so it's kind of sometimes hard to make sure that all the graphics are looking correct. But yeah, that looks correct to me. Where everything has been rotated correctly. Rotated in place 90 degrees clockwise. Alright, cool. Now, it might be helpful to, yeah, once we get down really tiny, everything starts to break down a little bit, but okay, cool. Now as far as what the rendering looks like for that data set, I'd say it doesn't really look that interesting, right? That's interesting that we can get that like that, but it's not really that interesting. As far as like procedurally generating from taking a random graphic and just kind of like resizing it and rotating it like that, I'd say that doesn't work very well. However, I was thinking it would be kind of interesting to, and this is where the thoughts from what I was drawing earlier kind of spawn from. It would be interesting to try to create an auto tile set from taking a series of graphics that were already drawn. If I drew out some patterns, what kind of patterns could we draw to make... Here, so let's do this. Let's open up Paint again and say that, so we have this thing where we're downsizing graphics. Now, the other idea was, what if we took a whole bunch of graphics and we, like, upsized them? Right, because if we look at our system names, Gent, right? You have Gent Common, Gent Down, and Gent Up, right? So if we look at Gent Up, generate tile upsize algorithms. Upsize and mix and match 16 by 16 graphics to create a source auto tile set. So that was the idea. So we're saying, hey, if we have a whole bunch of 16 by 16 graphics, can we kind of mix and match those to create some type of auto tile that kind of looks plausible, right? And if we're gonna do that, we're gonna need So I was thinking about, like, the Space Invaders algorithm that is kind of used on GitHub. So, like, on GitHub, if we go to GitHub really quick. If we go to GitHub and you look at your icon, the default icon on GitHub, which I still have on here. This is kind of created from just randomly generating some pixels and kind of mirroring them around. Just kind of cool. But that only gets you something that looks interesting at a small scale, right? When you try to do that at a large scale with too many pixels, that it just starts to look... You don't get anything that looks interesting. So if we're trying to, like, seed a data set for generating auto tile values, we can't use anything that is too many pixels. So 16 by 16, I'm thinking, is enough to, like, start drawing kind of, like, interesting patterns, but not so much to where if we just randomly seed it with data, that it'll just not do anything interesting, right? So the thought was, you could have, like, a series of many, many, many 16 by 16 tiles, right? So if we take, let's try to do, I want to do everything in terms of a 512 by 512 bitmap. So if we take 512 and we divide it by 16 for a second, right? Okay, we get 32. So we get 32 by 32 of these tiny little graphics, right? And a lot of games use 16 by 16 graphics, I believe. So if we look for, like, 16 by 16 game tiles, I think that's a pretty common 16 by 16. 16 by 16 is a pretty common thing here where people create kind of nice little tile sets using 16 by 16, right? I'm going to save this. 16 by 16. I'm going to save this in my notes. So So 16 by 16 is pretty common, right? It's enough pixels to, if you're skilled, it's enough pixels to do something interesting with, right? So you want enough pixels to where you can do something interesting, but not so many pixels that it's a monumental amount of work to get something done, right? Oh, really? Is Legend of Zelda actually 16 by 16, or is this just what size tiles did Link to the Past use? I don't think they used 8x8 tiles. Eight by 8 tiles? Well, we can take a look here. Hold on. Let's just take a look at this snapshot. Let's look at this for a second. Actually, no. Let's take this image. Save image as. So if we stop being stupid. Copy image address. Let's go to. We're gonna go to. I'm gonna go to Imgur and save this really quick. And I want to get. I think Zelda is probably using 16 by 16s. I don't think they would be using. I don't think they would be using 32s by 32s. Okay, so let me open that up and just take a look for myself. And see, hey, is this a 8 by 8? I don't think that's 8 by 8. That looks like a 16 by 16. Yeah, 16, well, I have 15 here, so I probably got off by one with my selection, or they have a little extra little space here. But yeah, so 16 by 16 is what's going on here. So I'm fairly confident that all these tiles, like all the art, is done with, 16 by 16, right? So this rock here is 32 by 32, but it's 4 16 by 16 tiles, right? So the idea is when we're making some type of graphics for... Oh, crap! Oh, God! I just saw some people... Oh, okay, hey, I guess I'll give up... Okay, so I was, like, I was in the middle of thinking here, and, yeah, so, yeah, is anyone new? I can give a quick tech demo rundown. Sorry, I was kind of thinking about, what I was, doing for a second. I'm just going to assume that the other person in the room here is new. So I'm gonna just go over a quick technical demo. I didn't realize I need to get like some sound notifications. Like I got the thing up here, but I can't see it sometimes. So here, I'm gonna throw this in here for a second. Sorry, I was thinking about tile sizes and how everything needs to pack into the engine and all that nonsense. But let's go to the technical demos really quick. and show you kind of like what I'm working towards. I'm trying to make like a fractal auto tiling engine, and what that entails is, well, first of all, you got to know what an auto tile is, and if you know what an auto tile is, the explanation is pretty easy. It's just, instead of drawing your subtiles of an auto tile set with pixels, you could draw your graphics with other tiles. So just take a normal graphic and replace all the pixels with just tiles, if that makes sense. So I made this game a long time ago. It's like a bomb game where there's explosions of different directions, and you can cause these chain reactions and destroy parts of the level. So I wanted to create an engine that is basically auto-tiling on steroids to facilitate more interesting level destruction, if that makes sense. So here's this little demo here. And we're just going to go through some of the tech that I'm rolling into this engine. Okay, so these are like little prototypes. These are prototypes for the engine I'm working on. So auto-tiling is usually done with kind of like sprite-based graphics, right? Where it's just like old school graphics. Usually when you think of auto tiles, or also known as rule tiles, you think of old school 8-bit games, 16-bit games, but you don't have to use auto tiling logic with old school retro graphics. You can actually do auto tiling logic with fancy shader code, as you are seeing right here, right? Now, the idea is that I want to make a 2D game with auto tiling, but that doesn't mean that I want the graphics to look old school. I actually want some really awesome high-def graphics that are quite intricate. And so I'm going to use auto tiling as the fundamental concept that the engine is built upon, but I'm going to take auto tiling to just a level that it's never been seen before. So an auto tile, if you're not familiar with it, it's I use a Wang tile style auto tile, which is the simplest version of an auto tile. I think it's just the most intuitive and easiest to work with. So the tile is aware of its neighbors above, below, left, and right. So the tile keeps a list of its neighbors, and it can have four neighbors, right? So 4 neighbors is 4 bits. Are you here or are you not here? Are you here or not here? Are you here or you're not here? Are you here or you're not here, right? So that's 4 bits to keep track of your 4 neighbors. So in a bit mask, 4 bits evaluates to the number 15. 0 to 15. So there are 16 different combinations for what can be around you in terms of your neighbors. So when you're making an auto tile, it has to be a strip of graphics where you have 16 graphics to account for all of the different possibilities for what your neighbor could be. And that's, I don't know if that's the best explanation for how an auto tile works, but I do have a resource for that. So let me see if I can find rule tile demo for a second, in case anyone is not familiar with auto tiles. I can kind of like, here, I'm gonna go into my shortcuts really quick here. Anytime one of my shortcuts does not work, so I have over 30,000 shortcuts. Every time I touch a piece of information that I find interesting, I put it into my shortcuts. And I don't have some type of like photographic memory or anything. The idea is that you make so many shortcuts that you go, if I were me, what would that shortcut be, right? So we're in a deterministic universe, and so we can just, we don't have to remember it. Okay, you get the idea? Yeah. So what I'm going to do is anytime I don't have a shortcut that I kind of wanted to exist, or I know it exists somewhere, I'm going to make another synonym. So these are all synonyms. So this, if I type this, or this, or this, it's going to give me a new shortcut. And I got to find that old rule tile video, which I know it's somewhere in my shortcuts, but I called it something else. So it might be called auto tile demo. It could also be called like, it might also be like called auto tiles explained or something like that. Okay, so auto tiles explained. This is probably the correct video. So I'm gonna go make sure this is the correct video, and if it is the correct video, I'm gonna send it in chat. So
what you're looking for, then you can.
Yeah. So this is a. So when they're talking about, I need to rewind more than I. Yeah, I'm gonna rewind to 11 seconds. So an auto tile is also known as a rule tile. So they're using a brush, and that brush has a certain tile set loaded into it. But that tile value is like an auto tile, and so it's a strip of graphics, and it correctly selects the correct one as you're like drawing with it. So I kind of think of it as a like, this person is using a material brush, is a way you could think of it.
Files will automatically update. If this is not what you're looking for, then you can click away from the video.
So the idea is that we just have these nice borders here, right? So I'm going to take this, and I'm going to put this into chat really quick for you. So Cold Blue Mist, if you want to take a look at that. I don't know if you're familiar with, so Cold Blue Mist and Ian, it's Ian Alexhart. I'm not sure if you're familiar with rule tiles, but if you want to take a look at that, then that video will give you kind of like a intro to what I am talking about. So now that I have that video in my notes, I'm going to go back to my notes and go, okay, next time I type rule tile demo, it's going to go to this video at exactly this time, and I won't have to be searching around mindlessly for it next time. Now, unfortunately, it takes a very long time. It takes about 10 minutes to reload my shortcuts because I've been literally adding to this for every day for 3 years. So there's just so much information in it that I can't always reload it. So I usually like reload at the beginning of the day. Okay, so let's go back to the technical demos I was showing you. So let's close this. So if you're not doing things in sprite graphics, right? So this is auto tiles, but not done with sprite graphics. You can do things like, I don't know, zoom in and still get awesome, sweet detail, right? So if we zoom in, right, we still get all this crazy detail. So this is not the fractal part of the engine. This is just one of the pieces of tech that I want in the final engine design. So I'm taking a lot of different proofs of concept that I've made over the years, and I'm finally rolling them into one cohesive engine design. So this is just one aspect of what I want to do. So let's go to like another aspect of what I'm trying to work on here. So right now, this is what you're seeing right here is a tile engine I wrote in ActionScript 3.0. And the tile engine has multiple layers, and those layers can be blended together. And so the tiles that I'm using are actually very simple tiles. I think each one of these tiles might just be 8x8 tiles. So think about an 8x8 pixel map, or an 8x8 bit map. You really can't make too many designs. But if you use those little, if you make tiny 8x8 auto tiles, and you draw with them, and you can blend them together, because you have different layers and different blending settings, you can start to get very interesting designs quite easily. So this is me just kind of fiddling around, and it didn't take me too long to draw this, right? It's just me kind of messing around, and I got something really cool with a minimal amount of effort. And after I made this tile map, I was able to apply different rendering settings to it. So I made this, and this rendering setting is called Foggy Morning. This one is Sunset, and this one is Starry Night. So it's all the same exact tile map, just with a different rendering setting applied to it. So when I'm thinking about my graphics, I don't really want to think of my graphics as, oh, they're just 8-bit tiles. I want to think of my tiles as actual materials. So I'm drawing with different types of materials, but the format of my material is an auto tile set, if that makes sense. Also, let's talk about data leverage. As an indie studio, you can't really compete in the same way with a AAA studio, right? A AAA studio can like hire hundreds and hundreds of artists. Well, maybe not hundreds and hundreds, but you know, well, no, maybe in the multiple. It depends on the studio, right? But as an indie studio, you're limited on your artist power, right? So once I made this, I could multiply my work effort by 3 because I can apply this rendering setting and I can apply this rendering setting, and I can reuse the artwork in a way that's not completely obvious, right? So I think that this looks sufficiently different from this and this to where the consumer of your game isn't going to be like, this is crap, they're just reusing the same art assets over and over, right? So you want ways where you can really leverage your time and productivity, right? So this is a threefold increase of productivity. So let's go back to the chat really quick in case anyone's saying anything. Okay, cool. So this was the old lighting engine I worked on. So I also do want to work on a lighting engine for this engine, for this new engine. But one thing at a time. So the first thing is just working on the base material editor, which is kind of what I've been coding recently. Here's the preloader for the old game, and then here is a tile set editor I made in Golang in SFML. So SFML is the graphics library that is built on top of OpenGL, and then Golang is just like Google's version of C, you could say. So after ActionScript died, like after Flash died, I had a really hard time kind of figuring out what programming language to use next, and it took me about 8 years to... I wasn't like constantly searching for something, right? But like for like 8 years, I had no clue where to go. And then I stumbled upon Go and thought it was pretty cool. And then later I read that, oh, Golang is just like a modern C. And I was like, really? Golang is just a modern C? And then I'm like, oh, wait, but I don't like garbage collectors. And I don't like this unsafe pointer business. So in my mind, I flip it on its head, and I think that C is a better Golang. Like, for somebody who cares about performance, the C language is actually just a better Go, which is like, I'm kind of flipping that around on its head, but that's kind of how I see it. Also, I'm very bad at UI, so I made like a little terminal down here for all my commands, because I'm like, okay, well, I can't just do everything with keyboard shortcuts. I need to have something a little bit more robust. So I just made like a little terminal that I could do things with, right? Type little commands and execute them. This tech will not go into the engine because it's triangle based, but it's kind of fun to show off. So it's basically a quad tree, but the quad tree is visually a triangle, right? Because if you think of the Triforce, 1, 2, 3, 4, right? So it's a quad tree. And you can click into the triangles and you can subdivide them, and it's going to pick a random color, right? And you can use this to kind of like make these kind of crazy snowflake designs. And then if you really want to get crazy, you can click and drag to just get patterns right away like this. And it's really fun, right? And you can just click drag really fast like this, and it's just like, you know, interesting, right? So you could throw down a little base pattern really quick by clicking and dragging really fast, and then you could hone in and put some like very fine-grained details in it, you know? Right? And be like, ooh, I have a thing, right? So that's fun, but it's not going to go into the final engine design just because, you know, it's triangle-based, and the data needs to be homogeneous, right? Like I can't really do things with triangles if the whole engine is based on squares. So I'm going to throw that in there. So my girlfriend is telling me it's break time. We'll see what's up before we decide to go on a break, because I know you just got here, so let's kind of go over more of the tech before I take a break. So I'm going to close this. Actually, here, let me put that in the chat, though, in case anyone wants to take a look at that. I can post a direct link to that. I'm going to close this. So here's a direct link to that snowflake maker if you're kind of interested in that. And I'm going to put this back up on another monitor, the chat. Makerworks Day. I see. Okay. Oh, thank you. Okay, cool. Cold Blue Mist, you've seen this before? So, there's a new piece of tech I have. So, let's go look at this. So, I need to create some, like, base materials for this fractal auto tile set. So, if you're familiar with fractals, a lot of times in a fractal, the way you render something fractally is you kind of, like, jump from node to node to node to node. To render something fractally. I don't know if that quite makes sense. But the idea with my fractal auto tiles is that instead of painting an image with pixels, you paint the image with like tiles. And then when you zoom into a tile, that tile is painted with more tiles. And then when you zoom into that tile is painted with more tiles, etc., etc., etc. So you're making these jumps from dataset to dataset to dataset, and that's kind of how you get like the fractal nesting, if that makes sense. So when you're doing computation, though, you don't have an infinite data set, right? You have finite computation. So the first part I need to work on is creating what I call terminal tiles. So we're going to create these fractal tiles that you can deep zoom into, but there's going to be a limit to the deep zoom. The goal is to have a deep zoom where we can zoom in to a molecular scale. So if we take the character and we try to like zoom into the character, I want the zoom to stop once we get to like an atom level, right? So that's kind of ridiculous, but that's kind of like the goal. So here on my left monitor right here is the data structure for how I'm storing the terminal tile designs. So I may have shown you a schematic diagram of this before, but this is an actual image with the actual data, and I'm going to show you how that looks when it renders really quick. I don't know if you've seen this before, because I just kind of got it working like a few days ago. But let's go edit some of this code really quick. So I was working with this image right here. I'm going to comment this out and use the other image. So it would be this image right here. So I'm going to take this right here, and we're going to recompile, and it's going to show you what this looks like in the current renderer. So let's give that a roll really quick and show you what that looks like. So what you're seeing right now is a hex dump. I have a pre-processing routine to turn my PNG files, my PNG assets, I turn them into hex dumps, and then I load the hex dumps into the source code, and then I compile the source code. So all these like numbers you're seeing back here is just that. Now I may need a way to speed that up sometimes, because I don't always need to re-encode the assets every time I compile. But okay, let's press P. And so right here, the renderer still needs some tweaking. So the four images you see here, like this quadrant, this quadrant, this quadrant, and this quadrant, are rendering as expected. These two images right here are just out of bounds, right? We're like outside of the bounds of the camera, you could say. I guess that's the best way to describe it. We're outside of the bounds of the camera, and whatever happens outside the bounds of the camera I didn't code for that, right? So I don't know why it's like this, because it's undefined behavior as far as I'm concerned, and I'll have to do some polishing or whatnot to fix that. But right now, we have like a very fixed camera size and fixed position, just to make sure that everything renders properly first. And then everything looks like it's rendering properly so far. So now the next part is to add some camera controls or whatnot. So that's the next thing I'm going to work on. But let's go look at this. So when you're seeing this kind of completely symmetrical graphic, that is rendered from this quadrant of the image right here. And then when you see this top right over here, that's rendered from over here. So this is the source data for that. And then down here, that's rendered from here. And then down here, that's rendered from here. So you might wonder, hey, this kind of looks like a MIP map, right? Like these kind of look like... It kind of looks like a MIP map if you're familiar with what a MIP map is, right? Because we have, we're kind of downsizing an image a whole bunch of times, but instead of just downsizing an image, we're actually using different images of different sizes. So you could think of these as levels of detail, but that's not really how they're used. Basically, we have a tile map that has different... you could say pixel sizes or subtile sizes. I don't know what you'd like to call them. But basically, for this graphic here, when you're editing it, when you're in the editor and you want to, let's say you're in MS Paint, right? And you can pick like different pixel colors in your pen. this is basically gonna, when this editor is done, it's gonna be basically just like MS Paint, but with a little bit of extra stuff, you could say. So when you change your brush size in MS Paint, it just says, okay, instead of painting 1 pixel, we'll paint, 2 by 2 pixels. Or if you make your brush even bigger, instead of painting 1 pixel, it paints, 8 by 8 pixels, right? Well, we have something similar going on, but instead of painting more pixels when you have a bigger brush, you paint bigger pixels when you have a bigger brush. So this biggest section of the data right here is the smallest brush size. So you need more tiles of a smaller size when there's... You need more tiles to fit the entire surface area if the tiles are small. So that's why the smallest tile size has the largest chunk of data, right? It's kind of inverted, and that can be kind of confusing to wrap your head around, that this biggest section is actually the smallest tile sizes. Or you could say that the biggest section is the most granular data, right? And then the tiles here are twice the size of the tiles here, right? And then down here, these tiles are twice that size, etc., etc., etc. And then eventually you get down here to where one tile is gigantic. It fills the entire canvas. So down here, in this area right here, you have one tile that fills this entire quadrant. So you might be wondering, like, why do I have, like, these 4 quadrants? Like, what's up with 4 quadrants? Why do you want 4 quadrants? Why do you want these 4 graphics? Well, let's go back to auto tiles. So auto tiles usually use 16 tiles, right? We're not going to use we are going to use 16 tiles, but we're going to do a lot of on-the-fly pre-processing of the data. So let me open up like a schematic diagram of the PAINT5D system here. So this schematic right here that you're looking at right here is a direct analog to this data. So this data set here, this is the explanation for, how that data set, what the names for the different pieces are, all that good stuff. So the reason we have, 1, 2, 3, 4 quadrants is because each quadrant is the data for 4 different subtiles. So this is the top left subtile, the top right subtile, the bottom left subtile, and the bottom right subtile. Now this subtile in the top right, if we're actually making proper data for the engine, would not be completely symmetrical like this. It would be a corner tile, right? So this is the right. So if this is the top right corner tile, this needs to be designed in a way that it looks like a top left corner tile. I hope I got that right. Sometimes I get my left and right mixed up, so I'll say that again. This is the top right corner tile. This is the top left corner tile, but the artwork for this is not conforming properly to the conventions of how we need to draw it, if that makes sense. So this asset here that I am rendering is more of a diagnostic asset. Like, it's not a final asset that I'll actually use in the engine. It's an asset for me to be able to check and say, hey, does the renderer render how I think it renders? It's just to make sure that the renderer is functioning properly. Okay, so let's say I said that the auto tiles I want to use, though, have 16 subtiles, and this is only 4 subtiles. So what's up with that? Let's explain that again. Let's keep this open here. So in order to get... So this little diagram here, this is the user view. This is the camera view, basically. And so this camera view here on my left monitor is a direct analog to what we're seeing on the screen over on the right here. So in order to generate the other 16 tiles, we can take different cross-sections of the data. Well, cross-section might not be the best way to call it, but if we want a top edge tile, we'll sub-select here, right? So we'll take a little bit from the left tile, a little bit from the right tile, right? If we want the bottom edge tile, we'll take a little bit from the left tile, a little bit from the right tile, right? If we want the left edge tile, a little bit from the top tile, a little bit from the bottom tile. Yeah, no problem. Oh, hold on, let me type this. Yeah, no problem. Like, I know that, some of this stuff, like, I am gonna get into the more interesting, explanations of how things work, but then after that it's going to be more kind of boring coding stuff. But I thought that since kind of new people are dropped in, I might as well kind of explain some of the new things that are going on and stuff. Right, so down here, right, if you want a bottom edge, oh, that was quick. That was quicker than I thought. All right. So down here, if we want to generate a bottom edge tile, we'll select a little bit from this bottom left, a little bit from this bottom right. Now, if we want a center tile, like a tile that is touching all of its neighbors, and we want to generate it from this data set, we can just sub-select a little bit from the top left, a little bit from the top right, a little bit from the bottom left, and a little bit from the bottom right, right? So if you see this kind of section over here that's kind of reddish, right, that would be our touching all tile, right? So the idea is, like, a lot of times when you're making auto tiles, it just sucks, right? Because to make an auto tile, you got to make 16 unique graphics, and a lot of times it's a very repetitive process where there's a lot of redundancy in the data. So the idea is to, and even this has some redundancy in it, right? Like you could probably just get away with, like, making one corner graphic and then rotating it 90 degrees, rotating 90 degrees, rotating 90 degrees, and then you'd only have to do 1/4 of the work. However, the more auto generation we have, the more redundancy you're going to see in the final artwork. So we need to carefully balance how to leverage our data, right? We don't want so much data that the artist... if the game engine has a certain amount of data in it that needs to be rendered, well, the artist has to do the work to fill out that data, right? So when you're making artwork, when you're, like, setting pixels to, like, draw a graphic, you're basically filling out data. You're basically filling out a data set. So that could be kind of weird to say that when you're making artwork, you're filling out a data set, but that's what you're doing, right? So the larger the data set is, the more work it is to fill it out, right? So we want to make sure that we don't make such a big data set that it gives the artist too much work to do, but we also don't want too small of a data set where the artist doesn't have enough information to do anything useful with, right? Like, for example, if we had a game engine that had 1-bit color, it wouldn't take long for the artist to make assets with it, because they can only pick a white pixel or a black pixel. But it wouldn't, so it would save the artist a ton of time, because they don't have many options to pick from, but it doesn't give them any tools either, right? So the resulting artwork might not look that interesting. So we need to carefully balance how we're using our data. So I thought that even though there is redundancy right here, where this corner could just be this rotated 90, this could be this rotated, these could all be rotated 90 from the same graphic. The idea is that I wanted to give the artist an option to make, if you look at, to make, like, maybe tiles that are a little bit different on the top and bottom. So let's look at, I don't know, let's look at, like, grass and rock auto tile. I don't know, let's just try something and see if we can find something really quick in, like, an image search. I don't know if that's gonna find what we're gonna look for. I know there was another, there's another thing I was looking at that, let me look at this web page over here, because I think it had something interesting. Okay, so this is a good example. Let's click this. So this has a good example. I'm gonna paste this in the chat. But can we click this and zoom in here? Okay, yeah. So notice with these auto tiles that we're looking at. Now, I don't know if they're actually auto tiles or if they're just very carefully placing them, but I can definitely see this, like, green, this moss and rock being an auto tile, right? And so it's not completely symmetrical around its perimeter, right? So it has the moss only on the top, and then it's just plain rock on the bottom, right? So when I was thinking about how much information I want my artist to fill out, I'm thinking to myself, hey, if this tile set wanted to be something where it's like moss on the top and rock on the bottom, we're going to need at least 4 tiles so that they can put like one some type of like greenish moss up here, and then they can put some rocks down here or whatnot, you know. But then after that, I think everything else can be kind of like extrapolated from that without losing quality, where anything past 4 tiles gets very redundant, right? So if you've ever seen, like, there's already like engines, or not engines, but like preprocessors that help you make auto tiles. And the idea is to make it so that people don't have to do any mundane steps to make artwork for my engine, right? They can just make those 4 graphics, and the engine, when the engine is rendering, it will dynamically create the 16 by 16 auto tile set on the fly, if that makes sense. Okay, so that was that's basically it. And then there was some experimentation I was working with. So let's look at the experimental thing I was just working on before I started giving a demo of the tech. So let's go into the PAINT5D system, and let's comment this one out. So this is just the keyboard binding. So P5D pattern right here is just the keyboard bindings for when I press the P key for pattern, I want to load a certain pattern into the engine so I can see what it looks like. And I was thinking that, hey, wouldn't it be cool to, if we keep all of our data homogeneous, we can have these happy coincidences where we can just pipe mix and match data in ways that it might not be correct, but it'll still run, if that makes sense. I can explain that a little bit better. So let's go into our assets folder. So lib, assets, and so the default data is this, right? This is a default tile set, and it's 512 by 512 pixels. And we're using every single pixel and every single bit of this. So what you're seeing right here, I kind of was misleading you when I said this is one auto tile set. This is actually 16 auto tile sets, but all 16 auto tile sets here are identical. So you might be scratching your head and wondering, well, how is that possible? Well, each pixel actually encodes 16 different auto tile sets. So we actually take a cross section of the pixels, and so this is actually, we're actually using 2-bit color. So if we look at this diagram in the PAINT5D system, I'm taking the alpha, RGB, and A. So the RGB and A bytes of a pixel, and I'm slicing them so that we're going to use 2 bits for one auto tile set, 2 bits for another auto tile set, 2 bits, etc., etc., etc. And then in order to get interesting colors, we're going to use palletized color. So we're using 2-bit palletized color, right? The idea is that because we have so much information here in terms of all of the physical designs we can make, that having a large color palette will make for too much information. Like, we want an engine that kind of facilitates a certain style of graphics and also doesn't give too many choices, right? We don't want too many choices, and it's hard to make something coherent in terms of artwork, and then not enough choices, then we can't make interesting choices. So I'm trying to design the engine to the sweet spot where anyone who is interested in art can just make something awesome, right? Where, like, you don't have to be an expert at art, where you have, like, you know, like, if you're an expert at art, you can be like, hey, I have my paintbrush, and I have, like, these, you know, hundreds of different colors, and I mix and match them. I don't want to give people that many choices, but I want to kind of gamify the asset pipeline in a way. I know that gamification is kind of like this cliche word that everybody uses, but I really want to, like, gamify it in the sense that, you know how, like, in a level design, the level is, it kind of gives you this illusion of choice where it kind of, like, even though it's, like, maybe an open world kind of design, it kind of guides you to a certain location. That's kind of how I want the engine to work, where there are choices you can make, but I want the design to kind of guide you so that you can make really awesome choices and make really awesome graphics. and the engine will kind of guide you, if that makes sense. That's kind of a weird way to say it. But okay, so this graphic here is 512 by 512 pixels. Well, let's find another 512 by 512 graphic, right? This is another 512 by 512 graphic right here. So this, so bear with me here. This is a valid tile set, right? It's a totally valid tile set, right? Because it's 512 by 512 pixels. We use every single bit, right? So, oh crap. Oh god, oh man, I'm just gonna be here for... alright, so, I might have to just do this over again. So, I guess I'll give another quick tech demo. Okay, so, here is... Yes, that tile set was unexpected, yes. So here is a... Hey, old Papa Pig. Here, let me, just throw that in there, because I know, why all uppercase on DOS? DOS? Like DOS Windows? So I'm not sure what you mean, Daddy. Dust? Is that like dust with like a silent H? But okay, so anyways, with our unexpected... I gotta eat. No problem, yeah. If you gotta eat, you gotta eat. Yeah, I'll see ya. See you around, Cold Blue Mist. So yeah, if you could clarify what that question means, I will be able to answer it. Dumb OS. Oh, God, dumb OS. Well, I'll uppercase, you're on dumb OS. I'm on, oh, I see what you're talking about. You're talking about this. It's, so that, okay, I see. I am, 35 or 36. I'm not sure, honestly. Yeah, so, all uppercase. So why is that? So it's actually because, with Windows doesn't give you very good control over font sizes in the Explorer, and it's gotten worse. Like, 5 years ago, you could change the font size, and now it doesn't even let you do that. So, because I can't be sure of what letters I'm looking at, I kind of defaulted just, like, everything's uppercase for file names, because I don't want to, like, accidentally be like, I think this file name is... Alright. I'm in Michigan, though, so... Yeah, so I didn't want to worry about the names of files, or like, oh no, I think it's, like, I hate the whole, you know, with programmer fonts, right? Programmer fonts, like I, J, K, and L, or not J, K, and L, yeah, I, J, K, and L, because lowercase k, uppercase k look kind of similar, the O's, uppercase and lowercase o, O's and zeros, I's and ones and L's, like, all that nonsense, right? It annoys me, right? And since I just have a basic Explorer up here, and I'm kind of doing my project in a very stripped-down way, I can't be making mistakes with just the file names. I mean, maybe it's an inconsequential thing that I'm just being too paranoid about, but I'm like, you know what? Screw it. Everything's uppercase. So anyways, right over here on the left screen is a default tile set, and it's 512 by 512 pixels. There's a certain scheme here to how the data is organized. It's organized in a very MIP map-like structure, you might notice, because we have, like, this section has big images, smaller images, and smaller images. Everything is kind of in a power of 2. And then I said that this is also a valid tile set, right? Because this is also 512 by 512 pixels, and we use every single bit of every single pixel to encode our tile set. Now, the thing is will we get anything interesting if we load this into the editor, or will it just look like complete nonsense? And that was a question I had, and that's a question we will find out soon. But I think there's a term called data normalization which I think usually that applies to databases, but I'm trying to do the same thing with my engine, where all of the important data sets are encoded as 512 by 512 bitmaps. And if I make sure to do that, then I can just mix and match things and just see if any happy, interesting coincidences happen. So let's go run the engine and see what that renders as. And the engine's still in its early stage. I kind of just finally, like a few days ago, got something interesting going. So I'll show you kind of what that looks like. If you see all that hexadecimal, that is the hex dumps used to embed assets into the engine. So if we hit the P key, it doesn't look very interesting, right? And you have to remember that this is a cross-section, right? This is a cross-section of every single pixel, right? Because I'm only using 2 bits per pixel for the tile set. So when we're looking at this image here, this image is technically 16 unique tile sets because we take 16 cross-sectional slices of every single pixel. And that's kind of weird to say cross-sectional slices of a pixel, but just imagine that, like, the bits of the pixel are like these little, like, I don't know, like stack of poker chips or something, right? And and each poker chip kind of represents 1 bit, right? So we just want to take a cross-sectional stack of like 2 of those poker chips, and that's the data for 1 coordinate within the auto tile that we're rendering, if that makes sense. So let's close this for a second, and let's put a better data set in it. A data set that kind of makes more sense, right? So obviously, this data set was not designed for the engine, and I gotta say, sometimes, no offense to Ayaya, but garbage in, garbage out sometimes. So if the data is actually formatted for the engine, you actually get a lot more interesting results. So let's fix some of the hard coding here. So right now, a lot of stuff is hard coded. I'm going to change what asset I'm dumping into the engine when I press the P key. So instead of using that image, we're going to use the image I actually designed for the renderer, right? So if we take that, and then we load, so we're going to load this one into the engine now. So let's go over here. Let's compile again. I probably need to change my build system around, because right now I'm hex dumping everything into the source code every time I recompile. I don't need to do that every single time. I only need to do that when I change my images, but that's a optimization for later. So now if I press the P key, right, we get something more interesting, right? Because this data set was actually, the data set we're rendering was actually designed for the engine, right? Now, these 4 quads that you're seeing right here are what you want to focus on. These 2 images right here, that's actually undefined behavior. It's like outside of the camera. And if it's outside of the camera, it's undefined behavior. I'm not accounting for how it's supposed to function when it's outside of the camera. Obviously, I have to do some cleaning up of the code and polishing and all that good stuff. But right now, the goal was to just use a fixed size camera, where this is the smallest camera size that can get all of the details without losing any detail. So this is a 256 by 256 chunk of pixels used to render this data set. And I wrote a whole bunch of test code for it. It looks like it's rendering as expected. So the next part is to add on some like camera controls. So the way this is going to work is this is actually an auto tile set. So an auto tile set is usually 16 tiles, if you're using a winged tile auto tile set. And I could actually find some information on that for a second. So let me see if I can look up winged tile auto tile set. Looks like that's not really wanted. How about winged tiles? Winged tiles. That is what I'm looking for. Let me just steal this and just add this as another entry really quick. Actually, before, I'm going to put this in the chat for you. So if you want to know, well, like, what wing tiles are, then you can take a look at that. So wing tile auto tile set. Okay. So auto tiles are also known as rule tiles. So I'm actually going to use a weighing tile scheme. So a weighing tile auto tile uses 16 subtiles to render. Now you might be wondering, well, I only have 1, 2, 3, 4 subtiles, so how am I going to do weighing tiles? Well, let's look at the schematic really quick. So this is the data layout schematic, and then this is what you could call the viewport schematic, right? So top left tile, top right tile, bottom left, bottom right, top left, top right, bottom left, bottom right. So if we want 16 tiles derived from this, then we can just take, cross sections isn't the best way to call it, but let's just call it cross sections for now. And if somebody has a better word for cross section, then tell me what that word is, because I don't know. Cross section is not the best word, but that's what I'm going to use. So let's say we want a tile that represents a top edge. Well, we would take a little bit of the left tile, a little bit of the right tile, and that would create a top edge tile, right? If we want to generate a bottom edge tile, take a little bit of the bottom left, a little bit of the bottom right, and now we've auto-generated a bottom edge tile. If we want the touching all tile, right, the tile that has neighbors on the top, bottom, left, and right, then we can take a little bit of everything, right? And, right, so that would correspond roughly to this, like, red region in the center of this rendered graphic. And the reason why we're doing this is, well, data costs memory. That's a horrible phrase there. Data storage has a cost, right? We have a finite amount of storage, so that's one reason. We want to be efficient with our bits, and a lot of auto tiles are just very redundant, right? There's like people have coded whole programs to auto-generate auto tile sets from a smaller set of graphics, right? So I would like to cut out the proverbial middleman and just say, hey, this engine is only going to require 4 graphics, and then when it renders, it's going to render on the fly using 16 generated graphics from the 4 that you fed into it, right? So I'm optimizing for I'm optimizing for memory footprint as well as artist time, right? Because if an auto tile set is 16 subtiles, but my artist is only required to create 4 tiles, then their productivity is fourfold, right? 4, 4, 4, and 4, right? Yeah? 4 and 4, 8, 8 and 8, 16. Yes, fourfold productivity. Or if you're into this thing called giving people a break, they're more productive and they can just, I don't know, enjoy life and do other things instead of spend that, that other 3/4 working on art. They can just do something else, with their life, So either way, we're saving people's time, and then what people choose to do with that time saved, right? Like if they want to crank out even more art, they can. If they want to just relax and do something else, they can, right? But we're going to save people time, right? A positive externality, I think, would be what you would call that. Okay, so my window code, I need to go into my low-level Win32 code eventually, because I don't know why it does this, but something about my window loop, it thinks that my window is not responding even when it is, and I'm thinking that I thought originally that maybe my message queue was slowly building up over time or something. I don't know what it is. I do know that if I were to press Control-Alt-Delete, the program would immediately function again. Like, I don't know why. Now, I can't press Control-Alt-Delete here because that will actually cause OBS to black out without my knowledge. So, like, you'll see black, but I won't see black, and then I'll think everything is okay. So, you got to make sure when you're using OBS not to press Control-Alt-Delete, or you'll have to restart your stream. But yeah, if I pressed Control-Alt-Delete and didn't do anything besides that, I just pressed Control-Alt-Delete and then just go back to the program will be working fine again. So that's why I think it has something to do with like a message queue building up or something, because I'm thinking Control-Alt-Delete probably like flushes the message queue or something like that. I don't know what it is, but I have to fix that eventually, because if I'm going to give this program to my artist, I can't be giving them a program that, oh yeah, if you stop working in it for a few seconds, the window code crashes on you. Like, that's not a good design. We don't want to, yeah. Unfortunately, that's the way it is for the time being. So that is really all of the... Well, there's one more thing. There's one more thing, and then after that, that's all the interesting stuff I have to show. So one more interesting thing, and then I'm just going to get to figuring some other things out, and it's not going to be that interesting. So I promise you one more interesting thing, and then after that, you know, I'm not gonna, I will totally understand if you go off and do something else, because most of the time when I'm coding something, it's actually not that interesting. It's just a lot of, like, you know, half of my code is unit tests, for example, right? Unit tests suck, and half my code is unit tests, so that means half the time I'm just like, I hate this, you know? So I was thinking that, you know, this data set, you know, it isn't very interesting when we try to render it. Is there a way we could take some random graphic and pre-process it to get something more interesting? So I'm going to show you that, and show you what I was attempting, and what I got when I did that. So let's make sure we have the right thing hard-coded in here. Yep, okay. Alright. So give this a run. I should have just used my console that was already open, but force of habit, well, most of the time I double-click my bash script. Okay, so... okay, we're going to load this. We're going to go over to the first subsystem. We're going to press P for pattern. And so now it still doesn't look that interesting, but it looks a little bit more interesting, right? Where it's like, hey, I can kind of see something now. I couldn't even see anything last time. It just looked like this blob of color. And now it's like, it's starting to look kind of like something at least, you know? So let's close that. But before we close this, I'm going to hit O for output. O for output is going to save the data set to disk. So whatever data set that I'm currently rendering, it's going to be saved into the mod folder. So let's go into the mod folder and see what I just saved. So let's go into mod, and let's go open up paint5d.png. So that is what I just saved, right? So the idea, let's look at both of our data sets right next to each other. So the idea was that this section is a top left corner, right? So if this is a top left corner, if we want to turn it into a top right corner, we have to rotate all the graphics by 90 degrees to make this a top right corner, and then we can rotate all these graphics by 90 degrees to make this a bottom right corner, then rotate all the graphics by 90 degrees once more to make a bottom left corner. And with this data set, it still doesn't look too interesting. Now, the thing is that we could probably try more tricks here, right? So with the graphic, we could try to warp. So we could try to warp her where we try to make the information density very high against this left edge and very high information density on the top edge. And if we applied some type of procedural warping filter, and then we rotated the graphics, we might start to get something that, you know, adheres to the rules of an auto tile a little bit better, and then it might render a little bit better. But this is just experimental. And I think that the time for experimenting has kind of come to an end, where I'm like, this is interesting, but I have a lot of experience trying to procedurally generate graphics, and I think that you don't want to go down the road of trying to get something awesome for nothing, right? Because if you want to get something awesome for nothing, you're really gonna have to... The only way I could see getting some type of awesome piece of artwork from procedural generation is you'd have to have some type of deep AI, right? You'd have to have some type of deep AI or some type of really heavy-duty machine learning algorithm. And then, even then, if you have a very heavy-duty machine learning algorithm, you're not getting something for nothing, right? Because a machine learning algorithm, to generate something, to generate data sets, it has to consume, it has to learn, right? So it has to consume, like, a very large amount of data before it can spit out something interesting. right? So there's no way to really get something for nothing. So we tried to get something for nothing by just saying, hey, let's just throw a random graphic in here, let's transform it a bit, and then let's try to render it, and let's hope we get something really cool. Unfortunately, that's not the reality. Unfortunately, what I've seen is that you can mix a little bit of procedural generation to help leverage the data you have, but you have to start out with some type of quality data in the first place. So you can use little tricks like, transforming things to help your data go a little bit further in terms of mileage, but you can't really just throw something at an engine and make awesome stuff come out. It just really does not work that way. I have tried many times, and it's like I think it can be a trap. It can be a time sink, right? Like we could put a lot of time into trying to take this image and do the interesting enough transformations to this image to make it like render into something that looks really cool. And we could do that, and it would become a huge time sink. And from my experience, it would not be a very fruitful effort. Now, there are things, don't get me wrong, like I said, you can do some procedural things that could augment your productivity to an order of magnitude. So, for example, what we could do in the editor is we could make a mirror brush, right? So we could make a brush where when you're drawing an image, it like mirrors your brush on like the X and Y axis, and then it like mirrors the brush radially, and then you could start to like make interesting patterns quicker. Like I'm definitely gonna code something like that into the editor. So there's definitely some procedural things you can do to augment and speed up the process of art creation, but in the end, you still need interesting data sets. We're still not to the point where we're getting there, but we're still not to the point where you can just have a computer do the job of an artist. We're not there yet, as far as I'm concerned. But we are getting there. But even when we get to the point where a computer can do the job of an artist, it's not going to be a few trivial transformations, right? It's going to be like heavy-duty machine learning algorithms that are, fed like huge data sets, and then it's going to be like deep AI, right? So when we're talking computers that are able to generate like art that actually looks good, it's not going to be me doing like a few stupid transformations or whatnot. Okay. So the next thing I wanted to work on was I had this like library for gent stands for generate tile, and com was for common. So this is my I just worked on the rotation code here, so this is like the rotation in place code. Then this right here was the code base or the sub-library for taking a big graphic and downscaling it and rotating it to try to create a interesting data set. And this is kind of what I just showed you with not this image, but let's go into our should have been in the mod folder. Is it in here? Yeah, so with this here, this code, or this image, the code responsible for generating that image is in here. So generate tile and dow for downscale, right? So we take an image and we downscale it, we rotate it, etc. And I'm going to close that. I'm not going to work with that anymore. This code right here, dump ass, stands for asset dumping. That was, my girlfriend thought it was funny, so we called it dump ass. Then there's another library called hardass, which is for hard coding assets. So one sub-library for hard coding assets, another sub-library for dumping the assets to different memory targets. I'm going to close that as well for now. I'm going to close this little ASCII diagram. I'm going to close this as well, and I'm going to actually push this up to GitHub right now. So right now it's in a state where that it actually compiles, right? So anytime I get like a benchmark where it can compile, I will push it up to GitHub, and I will push it up to both repos. I'll push it up to the private and public. So if you want to take a look at this code, and you have like Windows, if you have Windows 10 64-bit, you can take a look at this and compile it for yourself. Git status. Git add dot. Git commit -am. Rotation by 90 in place finished. Okay, so as far as commit messages, I'm pretty lax in my commit messages. I don't subscribe to, oh, tell me why you did what you did, and only that. Like, just make the commit message something useful, you know? As long as you're doing something useful and not just some blah, blah, blah stuff, I think you're fine. So let's see. Git status. Okay. Git push GitHub master. So we're going to push this up to GitHub. And then after we have pushed this up to GitHub on my private account, we will push this up to the Kanji Coder account. So git push Kanji Coder master. So yeah, if you want to take a look at that, it is on my stream in the orange text. The only orange text in my stream, that is where the project is hosted. So I think I can also put that in the chat. So git AAC URL. Yeah, so if anyone wants to take a look at that, they can take a look at that. I will say that my code is kind of crazy in terms of how I write it. Okay. So the next part I need to work on, the next part that could get the most like bang for the buck in terms of like figuring it out and getting it working, is editing the source code for the fragment shader. Before I edit the source code for the fragment shader, I'm going to put the... So right here, I'm going to put the tile set back in here. So the tile set, that's my diagnostic tile set. So this is my diagnostic tile set, right? It's the tile set I'm going to use to confirm visually that the renderer code is working properly. I'm just going to put that back in here. So when I press the P key, that's the tile set that's going to get loaded into the code base. I'm not going to change this for quite a while, so I'm going to exit out of here. I'm going to exit this now. I didn't actually add any code here. Originally, I was thinking we could do some more code where we try more tricks to try to auto-generate interesting tile sets, but from experience and from just my hunch, I just think it's going to be a time sink, and we should focus on the main engine design rather than getting distracted by all these little cool things we can do. So let's close that. We don't really need that open either. Okay, so this code right here is our GLSL code. And I have this little note, right? So I keep a pretty strict column limit, but when anything goes over the column limit, it's just there so I can notice it, right? So we can see this to-do message here. So I can kind of scroll through here really quick, and anything that kind of pops past the column limit is like, hey, get my attention kind of a thing, right? And this 14 is the auto tile set that is in focus in the editor. So right now, the editor cannot, we have keyboard bindings for switching between what tile set you're working on, but right now those keyboard bindings do not work because this number is hard-coded. And in order to fix that, we have to add some code to grab this number. So this number is not just encoded in a uniform, it's actually encoded into the texture, which makes things a little bit tricky, right? So once we get that working, it won't be too tricky to grab other values, but for right now, it's actually going to be quite painful. So let's put a little breakpoint here, and then let's scroll up here. So if you see this U sampler right here, uint sampler, right? So I'm encoding, all of my textures are unsigned integer textures because all of my textures are just encoding different like binary formats, right? I'm not actually using my textures as graphics, I'm using my textures as data sets. So since I can use unsigned integer textures, I'm going to take advantage of that just because it just makes things easier to work with. I don't have to worry about my data getting corrupted by converting floats back into an exact bit pattern, you know? So PAINT5D, this is the memory, the 512 by 512 memory for the PAINT5D system. And then we have a thing called tau depot. And tau does not actually stand for, what is tau? It's something related to pi, like if we're talking about math. But that's not what it stands for. It stands for texture as uniform depot. And And the T is silent as well as absent. So tau depot, right? So tau texture as uniform, TAU, and then depot as in like a warehouse or whatever, right? So just if you haven't noticed already, all of my names are basically either 3 letters or 7 letters. Because part of that's because I am very OCD about making sure my code lines up, and then the other part is reducing the amount of mental search space, right? So if I want a certain variable, if I can keep my variable names very short and keep them to a very specific pattern in terms of how I name them, then it leaves less for me to remember, or makes it easier to recall what the name of something is, if that makes sense. Because if you've noticed already, I'm coding all of this in PAINT5 in Notepad++, right? I'm not using like a fancy editor or whatnot, and so this is my I guess you could say my coping mechanism. I'm kind of I've described this before, but I'm kind of a pocket knife person as opposed to a blender person, in the sense that I'd rather have very simple rudimentary tools and just be very skilled with those simple rudimentary tools than to kind of have this cognitive overload of having a whole bunch of very specialized, complicated tools, if that makes sense. I'm a minimalistic person, which I don't know if that's a lie or not, because it's like I say I'm minimalistic, but then I do this crazy stuff. So also this code, I said it was the fragment shader code, and you might look at this code and you might think to yourself, well, if it's fragment shader code, shouldn't that mean that this is GLSL and not C99? And when you're looking at this, depending on what you've seen so far, you might look at it and be like, this isn't GLSL, it's C99, and then other people might be looking at this code, and then it might be saying, no, it's this isn't C99, it's GLSL. Like, you might, depending on what you're grabbing onto as you kind of look through this code and glance at it, you may come to a different conclusion as to what language is being used here. And the answer to your question is, if you have that question, is this is actually C99 and GLSL. It's actually written in a very generic way so that it compiles both as valid C99 code and both as valid GLSL code, right? So the reason we can get away with that is because we can just do really fancy things with macros. Because the syntax for macros is the same in GLSL code as it is in C99 code, right? So any kind of what do you call it? So any kind of so I've seen you do this a few times and I still don't understand what that's about. Did you balance those brackets somewhere else earlier in the chat? But yeah, so yeah, all we gotta do is use defines to kind of like edit the code in ways to make it either valid C99 or make it valid GLSL code, right? So we have a macro called this is OpenGL, right? Oh, I got ya. Okay, fair enough. Yeah, so got ya. Okay, so we have this macro, is it OpenGL, right? We have an if-def, is it OpenGL code? And if it's OpenGL code, we're going to do a lot of very specific stuff that goes on the top of your shader, right? So, right, you got your uniforms and all that good stuff, right? Then further down, we have some macros that always exist. So, this macro here is because the way I pre-process this to get it into a shader is I just wrap every single line inside of double quotes. Now the problem with that is that means that this source code cannot contain any double quote characters. If this source code anywhere in the file contains a double quote, it will destroy my build system. But then I have macros for creating error messages, and typically when I call my error functions, I give it a hard-coded string. Well, that creates a problem because I can't have strings in my code. Well, I can have strings in my code, but I can't hard code them with double quotes. So the way I get around that is this is the stringification preprocessor token. I don't know if I'm describing that correctly, but one little hashtag here means it's going to take this variable and surround it with quotes, right? So this way we can get a quoted variable into our code without actually using quotes, right? So this stands for, ES stands for air string, I believe. It looks like if we want to actually know exactly a better explanation, it looks like video 112 at 56 minutes and 50 seconds will kind of explain how that actually works. Okay, so then down here, right, if it's OpenGL code, float32 is float, u32 is uint, IVEC2 is IVEC2, UVEC4 is UVEC4, and then let's specifically look at these two, because I think these are the most interesting things, or the things that will kind of explain this, even though I'm kind of beating this into the ground. If we're running as C99 code, we have to use a polyfill, right? So integer vector is not a thing that just comes with C code, right? That's not like a default thing you get out of the box. So we have a struct for that, and you'll notice that there's this namespace called polyogl. Polyogl just stands for polyfill OpenGL. So it's anywhere I need some type of polyfill, I use that. Now, I don't know how common the term polyfill is. I take that term from JavaScript, right? So JavaScript has this term polyfill, where it just means that they inject something into. Usually, it means you're taking an older version of JavaScript and you're kind of injecting some type of functionality that exists from like a newer version of JavaScript, right? You're injecting some type of functionality, right? So I thought that. In terms of what I was doing, it seemed to me that the term polyfill just made the most sense. So this namespace here is where I put all of the polyfill code, right? And so far this is working. Now, the thing is, you have to be very careful when you're doing this, right? Because if we get this code wrong, so if we get this code and this code wrong, then we're going to be in a world of hurt. And what do I mean by that? So because we can compile as both C99 code and GLSL code, that means we can run unit tests on our GLSL code, right? We can run unit tests on the CPU side to confirm that our shaders are correct. And that means that we don't have to do a whole bunch of guessing and checking and building up our shaders at a very incremental one small piece at a time. As you usually do when you do shaders. If you have any experience writing GLSL shaders, it can be a very tedious process where you have to be like, okay, change this one pixel color and confirm that it changed how you expect. Okay, change this other little thing, make sure it, right? You have to do all these little twiddling things on your way to build the final shader, because you have to keep on confirming that your mental model of your shader code is correct. And it can be a very tedious process. I would like to avoid that. So rather than doing that kind of tedium while I'm building the shader code, what I do is I can compile it as C99 code, write a whole bunch of unit tests to make sure that the math is correct, and then I can just run it as shader code, and the shader just works out of the box, right? So my shader just I did not have to do any debugging of my shader code to get what I have on screen, because I already unit tested it as C99 code, and I was very careful about these. But if we screw this up, right, if we screw this up and we screw this up, we're going to be out of luck, right? Because if we have the correct macros for the C99 code, but then the macros for the GLSL code are incorrect, what will happen is our unit tests are going to pass, but our shader code would still be incorrect. So we have to be very careful about what these polyfills are, right? So for example, like if we take this define for UFF, which is a uint FF, and we change that to like 0x80, we would get some weird behavior, and it would be very hard to hunt down. So we have to be very careful about this, right? Or if we swap the texture memory, right? So this tau points to this texture memory, this P5D points to this texture memory, right? If we screw that up, we're going to be in a world of hurt as well. So if we look at tau, for example, so tau and P5D, right here, they're just a 0 and a 1. And when they were compiling a C99 code, this is an enumeration to find the correct CPU side texture, right? So this is 0 for this CPU side texture, and this is 1 for this CPU side texture. So when we're running the unit tests on the CPU side, we have to use the bitmap that exists on the CPU side. And then when we're running as GLSL code, these are the textures that correspond to those bitmaps. So tau depot is the CPU side bitmap pushed up to GPU memory, and then same thing with PAINT5D. PAINT5D is the CPU side bitmap for PAINT5D pushed up to the GPU. So yes, if we were to accidentally flip these around, we would be in a world of hurt. And that also gets to the point of, like, why do I align all of my code so meticulously? The reason I align my code so meticulously is because despite our best efforts of, like, writing tests and all that stuff, I almost said nonsense, but it's not nonsense. Tests are a great idea. Write tests for your code. If you don't already write tests for your code, write tests for your code. So despite your best efforts of, like, testing your code and maybe linting your code and doing all of these procedural things like compile time checking, right, having very strict compilation settings, despite all of your best efforts, there are always going to be things where it comes down to the last line of defense, which is you. So by lining everything up very nicely, making like little checksums, right? We got a 20 here, and we got 1920 here. By lining everything up very nicely, we can visually lint the code, right? So we can look at the code, and we can glance at the code, and we can see if anything immediately looks out of place, right? Because sometimes, not all the time, we hope that it doesn't come down to this, but sometimes it does come down to there's a bug in your code, and it's not detected by your unit test, it's not detected by the compiler, and it comes down to just looking at the code and seeing if it looks correct and finding the error there. So by meticulously organizing your code, you can help alleviate that problem a bit. Obviously, it is a lot of work to write code in this kind of meticulous way, and so you might not think it's worth it because it's a big time sink. Totally understand. Because it is, it's a thing that does take a lot of time, right? So, okay. So, we want to kind of sample from this memory here, this tau depot thing here. And let's just look around and see if we're referencing it anywhere else, or if it's kind of just stubbed in here. So, it looks to me, if I take a quick look, we should be using tau when we reference it. It looks to me that nowhere in this code are we actually using this yet. So we're going to need to add that functionality in here, and we're going to have to figure out where the function goes. We're going to have to figure out what to call that function, a whole bunch of stuff. I think the first thing we could do is we could look for PAINT5D and kind of see, like, well, what do we call the PAINT5D function for sampling from, okay, PAINT5D bitpack get. PAINT5D 10GL Texel fetch. Okay, okay, P5D 10GL get. Okay. So let's look at the CPU side versions of the functions, and maybe that'll give us a little bit more insight as to what we should be calling these variable names. So let's go into tau depot really quick and look at the data and the functions. And do we have any notes? No. Okay. So right at the top of this file, we have what I would consider the most important functions of tau depot. These three variables are to locate the specific pixel for where you're encoding the data. And then this is your payload. So your payload is actually 4 pixels. Now, if we're only encoding a 32-bit value, we'll only use one of these slots, and the other slots will be unused. With that, we see this is called tau depot put, this is called tau depot get. My first thought is just to say, okay, let's rewrite it, and give it kind of the same name, and we could double namespace it. We could do that. Or if we look at the namespaces in here, it looks like everything is namespaced as P5D 1OGL, right? That is the case. So I think it would be sensible to keep the same namespace in this file, because it looks like this file has the same namespace everywhere. So let's see, text will fetch U32 var. Okay, so it looks like we're gonna have to make use of this text will fetch variable, and then inside that text will fetch, instead of using PAINT5D, the PAINT5D texture sampler, we're going to use the tau. So let's steal what we want from here, and then kind of like use this to build up what we're doing, right? So let's kind of steal this. Actually, let's steal this whole function really quick. Let's steal this, and let's paste this here. And do we have like a notes file? Oh, let's just okay, let's remove this so we can open this up and work with it. So we know we need this. We know we need to go like this, and we need some type of coordinate. Right, we have to do a text will fetch here. So U32 var. So let's steal that. And glow is like the XY, right? So we know that we need invect2 glow, and that's the global coordinate on the texture. So we need some type of function that's going to take these coordinates here, and it's going to convert it into a global pixel coordinate. So let's think about what we're going to name this. So I'm going to call this, I'm going to call it we could do this. We could just triple namespace it, which is kind of confusing, right? But we see tau depot get, right? So if we want to find something else called tau depot get, then we could find it, you know, if we just search for this here, we can find it everywhere where it is, right? I think this would make the most sense because of what we're doing. Now the thing is that we can't do any type of weird pass by pointer, pass by reference, whatever you want to call it. We can't do any of that stuff in GLSL code. So you see how this function is written. It has output parameters. We can't do that in GLSL code. So we have to change how the signature, or the prototype of this function, to always pass things around on the through like registers, right? So let's do this. Glow equals some tau depot math function here. So we need some type of math function here. For this get, what we're gonna do is we're gonna take let's just steal some stuff here. Actually, no, let's go look for this for a second. Let's see what the variables are called in the actual function. So also, you'll notice that these are 8-bit integers. We're going to do everything in 32-bit integers in the GLSL code, just because we don't really have the luxury of specifying bit widths when we're doing GLSL code, right? So we'll steal this, though. We can steal this kind of declaration here. We can steal that and paste this in here. And that is kind of long, so we might want to change what some of these variable names are to something a little bit more palatable here. So this is going to be a U32 now. And this DEX, whatever, right, we use these variables so that we know the range of them, but this is a very long kind of like, this is a very, instead of encoding the range of the variable and making this ridiculously long variable, I think it might be a little bit easier to just say assert, and we have to use assert as a macro, so we take it out of the GLSL code because we can't actually assert in C90 in GLSL code, right? So we just assert that dex tau. Do you want to just call it dex tau, or we could just call it tau, right? You could call it lowercase tau. I'm going to call it dex tau, though, just so that it's a little bit less confused with this variable here. And we're going to assert this. This is, greater than or equal to 0, and dex tau is less than or equal to 16 minus 1. And the other thing we have to make sure of is, even though this assert is going to get stripped out of the GLSL code, I have found in my experience that if this code in here is improper, the GLSL compiler will still complain. Even though this macro is going to remove whatever is in here when it's compiling as GLSL code, this code still needs to be correct in terms of being proper GLSL code as well. Which is kind of confusing, but from some of the trouble I had earlier to get this code to work, I know that that is what I'm saying is in fact true. I don't know why it's true, but it seems that these lines get evaluated by GLSL before the macro strips them out. I have no clue why that's true, but that is the case for my setup. I don't know if that's always true. I don't know what the spec says about that, but that is the case here. So we'll change this number to 256. And so you notice that I kind of write my code where I have, instead of 15, 15, and 255, I wrote -1 here. And that's just so that I can see here, I know what the numbers are, right? Like 15 is a more confusing magic number to look at than 16, if that makes sense. Because I can look at 16 and I'm like, oh yeah, because there's 16 of these subdivisions. There's 16 of these subdivisions, and there's 256 of these subdivisions. Okay, so we can take these asserts here, and then once we have these asserts, then we don't really need to verbosely encode the range of the type in the variable, right? Now, I'm going to keep this example here because we actually are going to need to reference this eventually as we're writing out this code. Where do we want to save this? Can we save this as like P5D OGLF? I'm just gonna name this scratch, right? So I just want to save this somewhere, right? So it's not production ready code, right? It's all broken and we're thinking. So I'm just gonna name this as scratch, and I'm never gonna compile this file, right? This is just gonna be where we're gonna think out the logic and assemble something together that's coherent. So one of the problems with this getter is that if we look at this getter over here on the right, it has 4 output parameters. So if we have some type of piece of data that has 128 bits, then we use all these slots, right? So 32, 32, 64, 64, 64, 128, right? So if we need 128 bits of data out of here, we'll have to look at all 4 pixels and return all 4 pixels. Now, we don't always need that much data, right? So, for example, the active auto tile set is a 32-bit value. So if it's only a 32-bit value, it's encoded in the first slot here, and then these slots have the data that's here is undefined, right? But we only need this slot here. Now we have to remember that because this is GLSL code, if this function is going to both pass 128-bit values and 32-bit values, then we would have to pass a struct that, holds all 4 of these 32-bit values, right? And if we're going to use this quite often to only pass around a 32-bit value, we really don't want to be using up 4 times the bandwidth. So in order to fix that, we're going to call this one get U32. And this one is going to be used to fetch only pieces of data that are encoded in 32 bits on the texture memory, right? So on the Tau Depot memory, I have encoded viewport rectangles, and those viewport rectangles are encoded as 4 pixels, and those pixels encode the top and bottom bounds and the left and right bounds of the viewport, right? So 1 pixel for each one of those things, right? 4 32-bit values. So we're going to write this function specifically for grabbing only 32-bit values. This function is not going to be able to grab the camera position. It's just going to be specifically written. Right now we're going to write it so that we can get access to the active auto tile set in the editor to change what is rendering depending on what buttons we're pressing here. Okay, so we got tau sub var get U32. So we've named this in a way to where it's similar enough that we can cross-reference it with this file, right? Because it's basically a rewrite of this function, and therefore we want to keep the name very similar to this, right? Now the name spacing, I'm not really a fan of the triple name spacing here, because usually I do double name spacing, and now this is triple name space, and that's kind of like, why? But it's a priority of mine to know where, you got to be able to find your way around the code base. You have to figure out how all the little parts are connected, and because of that, I might be annoyed that this variable name is too long, and it has too many namespaces and all that stuff. But at the end of the day, I need to be able to read the code and know how the things are connected. So that sucks that it's kind of like an oddity where, 99% of my stuff is double namespace, but now this is triple namespace. That sucks, but the visual weirdness of the code, or things that I don't like visual, that's a lower priority than being able to find my way around the code base and understand my code. So, oh well, I guess. Okay, so we know there's going to be some type of function here to get this global XY coordinate on the texture. Okay, once we have that global XY coordinate, we're going to use the texel fetch function that we already wrote, and it's going to load it into the U32 variable, and then we're not going to do any of this stuff here, right? This stuff here, we already got the pixel that encodes the value, and we're not slicing up that pixel, right? So in the original function we stole this from, we were slicing up the pixel. That's not the case here. We just want this U32 value. So if we want to be more specific, no, actually it's different data depending on what values go in here. So U32 var is actually the best thing we can do. So we can make a little note here. Right here, return value encoded in Tau Depot memory. And then we can make a note, tau, texture as uniform. So there's a limit to how many uniforms you can have in a GLSL shader. So there are some basic uniforms like iMouse, iResolution, and iTime that I actually implement as actual uniforms. But after that, everything else, any other type of uniform that I need, is going to be encoded into a texture so that I don't have to worry about limits, right? Like if I want, 1,000 uniforms for something, I'm going to have those uniforms. And I'm going to use it by, encoding them into texture. So texture fetches are relatively efficient because, shaders are kind of like doing that all the time. Now, I'm not a, what do you call it? I'm not a, GPU architecture guru here. So I can't tell you any more than that, because I don't know any more than that. I just know that memory access on a GPU is faster than what it would be on the CPU side. So some things that you might be like, this is doing a lot of memory access, it's not going to run very fast. Well, because it's the texture fetch, it's going to run faster than we expect. Well, I guess that's kind of, well, it depends on what you expect. Anyways, so far it's working okay. Well, I mean, if things start to break down on us, we'll have to reconsider our life choices. So another thing is that because we're encoding this code into a string, the column limit for this is actually going to be 1, 2, 3, 4, right? We don't want to hit exactly this edge here. We actually want to be 4 away from the edge because we need some room to like wrap this in a gigantic string when we're pre-processing it. And so that kind of sucks. Okay, what else? Okay, so now we need this function, and so let's look at this. So pixdex, so this is getting the pixel index. Not the pixel XY, but the pixel index. And what's going on here? This looks like we are manipulating the index in order to get the correct, looks like, well, it's labeled component index. So pixel index. So it looks like we're taking the pixel index and we're doing some math to get the top left. Okay, yeah, I see what's going on here. So we're getting the 4 pixels that are encoding the value. But if we're only trying to get a uint32, we only need like one of these values. But it's important to know. Oh, got you. So this pixdex gets the upper left pixel, and then all of our information is encoded in these 2x2 clusters of pixels. So after we get the upper left pixel, we want to figure out what the other 4 pixels are, or the other 3 pixels, right? Because this is +0 and +0, so this is the original pixel from here, and then these are the other 4 pixels, or the other 3 pixels, sorry. So we want something kind of like this, but it's only going to do this. So we know that instead of using get pixel index, so there's a little bit of incongruity here, right? So on the CPU side, everything's encoded in bytes. So we have to make sure that we account for the fact there's a difference between a pixel coordinate or a pixel index and a component index. Like, does that index tell us which pixel number we're on, or does that index tell us what component number we're on, right? So generally, to take a pixel index and convert it into a component index, like R, G, B, or A, we need to just multiply by 4. That's what's going on right here. So we have this function, and we need something like this function, but instead of getting a pixel index, we need to... Well, actually, it's already getting the pixel index. That's what we need, right? I don't know if we really need to get the pixel index. I think maybe this function right here, this function on my left monitor, I don't think needs to map to this. It needs to map to something like this, but instead of getting the pixel index, I think we just need to get the pixel XY. Oh, I can see. Oh, I see. So if we get the pixel index, we only have to use one number, whereas if we're getting the XY, we have to get two numbers, right? And then we're using twice as much bandwidth in our shader, right? For that specific variable. So okay, so I see why it's that way, and I'm gonna say, you know what? I think that makes sense. And let's steal this for a second. So let's take this and say, okay, this is gonna be int32 pixdex, right? We're gonna whenever we use a variable, if the variable means the same, if the variable is the same information, then it needs the same name, if that makes sense. So same information, same name. So pixdex, and then we're going to take this, and this doesn't actually exist yet, right? Now it's a private function, and I think that is actually fine. And we're going to say AAC 2020 P5D 1 OGL Tau Depot Pixdex. Really, so it's just called Pixdex. So it's not even called get Pixdex. It's just called Pixdex. Now I question my naming convention here. Like, why do I just call it Pixdex instead of get Pixdex? But even though I'm like, oh, it would make more sense calling it this. But the thing is we want to keep like we want to keep enough similarity with this function name and this function name here. So maybe later one day we decide to go through the code and clean it up, and at that point in time we'll change this function name and this function name. But right now we want to make it very obvious that this function name here is somehow derived from this function over here. So we want to be very careful about the naming here. So this thing here, and then up here we can say, you know, int32, and then we can take this, and it's all the same parameters, right? So it's all the same parameters all over again. Okay. And let's put a little dash between here, or actually, no, let's... I'm thinking about it. I2. Okay, sure. Let's put a little divider here, so we can make sure that we never exceed. We never want to exceed right here, right? While we're writing this, because we're going to wrap it in a big string later. Okay, so now that we have that, we can take this name right here, we can put it up here, right? Cool. Now, what's the next part here? I guess we have to do some logic in here. Once we do the logic here to get this index out, so this is, so right, this is, pixdex equals, and, you know, I'm not very consistent about this. Like, sometimes I'm like, oh, I totally like this Pythonic kind of indentation style, and then other times I'm like, oh no, do it like this, and that sucks that I am a little bit inconsistent. But lately I've been leaning towards this style, because it takes up one less line, and then also you can't accidentally, if you write it like that, you can't, like, if you write the code like this, you can accidentally do this, and then things blow up in your face. And so if you write it in this kind of like Pythonic indentation style, you're not going to make that mistake. Some people might hate this because, you know, your brackets aren't completely symmetrical or completely lined up. But But lately I've been liking this style, so I'm going to stick to that. So pixel index is going to equal this. And then once we have that pixel index, we need to get this global pixel location, right? Because we need to do a texel fetch on it, right? Well, in order to do that, we need to do an index to xy location function. So we're going to do index to xy. Actually, I should have done... So this is a very old snippet. It's originally written in Golang. And I just realized that this is not going to work for us because we don't have a modulo operator in GLSL code. So I probably have, if I'm lucky, I have an index to XY GLSL. Like, if I'm lucky. And there we go. I have an index to XY GLSL. I've already written it. So the trunk command, we have an F for float, number of tiles on the X, TY, so let's kind of rework this a little bit. So it's going to be hard-coded for 512 by 512, so let's just put a 512 in here. Oh, boy, that would be bad. 512. Let's put a 512 in here. And I'm a little bit paranoid because that... Is it really like that? Okay, I guess it was like that. 512 and 512. And I don't know why I... There we go. So 512 and 512, because this is the width, right? So, okay, so we turn this index into a float to do this division, then we truncate it. And then that gives us our TY, and then whatever is left over is our X. That makes sense. So where it says DEX, we're going to copy this, and we're going to say, oh, you are now PixDex. Or we could change it around right now because we're running out of room. We want to keep this kind of terse. Or we could do T for trunk, right? Well, we'll think about it. So, PixDex. So, 1, 2, 3, 4. And 1, 2, 3, 4. So we need to stay... We can't go past that. I think we'll be just alright. If we just do that, we're just in the clear there. Though it is still kind of like a little... but we still gotta fix that. Let's just do... define D and do PixDex. And I know that in my code, I'm not using any one-letter defines on section dividers, so I can do this. And then, so F and D. So undef. Alright, so basically, we got a snippet, right, for how to do this, and then we can kind of rework that snippet to our heart's content for this kind of code here, right? So it's not going to be 1, 2, 3, 4. So having a snippet is just a good way to get a good starting point and make sure you don't do anything stupid mathematically, right? So even though I've typed out this formula many times, I want to reduce the probability that I'm going to make some type of math mistake. So because I have snippets that I've used many times, I can paste the snippet, and as long as I carefully replace variable names, the code should be mathematically correct. That's the whole reason for having snippets. Well, not the whole reason, but one of the major reasons. So we got int tx, int ty, and those actually are going to be locations in the UVec. So this UVec here, IVEC2, sorry, I said UVec, IVEC2. So instead of saying tx, ty, we could just directly use the vector. So instead of wherever we see ty, we can go glow.y and glow.x, right? So let's change this to glow.y, and this is also glow.y. And then here is going to be the x, because we see tx, so glow.x, glow.x, right? So we've refactored that. Does everything look nicely lined up? It isn't quite nicely lined up. Let's line that up nicely. And now that we have this, what I think would be nice is to make this a snippet as well. 1, 2, 3, 4. Make this a snippet as well, because now we have a index to XY GLSL, but it specifically works for an IVEC 2, right? So it might be nice to, in the future, be able to reference this and be like, hey, I have a snippet for this. So let's put this over here, paste it, and then remove the indentation here. And we'll call this index to XY. So let's go into our auto hotkey folder. And it's GLSL code. So let's see if we have a GLSL folder in here. GLSL. GLSL, yeah. So we have a snip folder and new folder. And this is index to XY IVEC 2, right? So index to XY, so IXY IV2. So we're going to put this in our shortcuts. Index to XY GLSL IV2. I'm going to put an IV2 on it, on the little name here. I'm going to put that in the name, and I'm going to use this verbatim as a shortcut, right? So we're going into the code here. We can say, if we type this exactly, it'll get what we're looking for. And then we can also do this, and then we can do ITXY, index to XY, GLSL IV2, or ITXY IV2, or index to XY IV2, or index to XY IVEC 2, or index to XY IV2, DEX to XY IV2, DEX to XY IV2. So now the thing is that, right, there's many possible combinations for what we can call this, and the longer the shortcut phrase is, the less likely that we're ever going to ever type it correctly or remember it correctly or all that stuff. So what we can do is we can, let's see, we can make all of this route to some master shortcut in order to help reinforce our memory, right? So we have all these vague phrases that we could type, and then we could route it to one specific keyword, so that every time we guess, it reinforces our memory to a very specific phrase. So I'm thinking, you know, we already call it IXY IV2, so how about use IXY IV2, right? So index to XY IVEC 2, and have a little explanation of what this kind of thing means, right? And then what we can do is right here we can say type it like that, but then also remember that I'm probably not going to want to type it in all uppercase, so we can make a lowercase version, TLCMD, and then we can also make an IXY IV2 with a dash, IXY dash IV2, and then IXY IV2 like that, and then also IXY IV2, and that kind of covers all of our bases, right? So anything like that is kind of acceptable, all right? So any other synonym is going to route us to this phrase here, and that phrase is the one that's actually going to give us the shortcut. So if we come back to this months and months later, we're probably not going to remember the phrase that we have in blue, but we should have enough phrases here that it can hint to where we need to be, right? So also index to XY, do we have, how about index to XY GLSL, right? We already have that, right? So I think that right now, we need to change the index to XY GLSL code for a second, and say, XY GLSL, IXY GLSL IV2. So we need to make our shortcut a little bit more specific. So this was the original shortcut, right? So now we're going to say, we're going to take this one here, and we're going to say this one is technically index to XY GLSL I32, right? IXY GLSL I32. IXY GLSL I32. So I want to say, if we're over here, I want to give you the option to pick index to XY GLSL I32 or index to XY GLSL IVEC2, right? So have these options for either this one or this one, because now we have two different snippets that give us kind of a similar thing. Also, let's make lowercase versions of all this. And then let's also make snake case versions of this. So let's paste this and go to snake case. And then we got my to snake case snippet doesn't work exactly correctly, but there. So now we have all these kind of like synonyms here. And that was the wrong thing anyways. Crap. Let me try that again. Let me give that another shot. 1, 2. TL CMD. My bad. So I meant kebab case is what I meant. To kebab case. To kebab case. Okay, there we go. And then we kind of clean this up a bit in our shortcuts. And all of this can be kind of like very redundant maintenance, but I think it's important, so. That looks good. And we can make a note of this. And this needs to be paste file. So we gotta paste this file, and this needs to be paste line. Paste line. Paste line. Okay, so now this thing here, I don't think we have that as a shortcut yet. Oh, we do. It's right here. Okay. And do we have, I don't know, IXY GLSL? I don't think we do. IXY GLSL. IXY GLSL. IXY GLSL. Okay. Okay, cool. So the next time we do this, we have, we can find the other version that we rewrote just now, and it'll be a little bit easier. So paste line, this is a paste file. Okay, and then we'll make a little divider here. And we'll go put this back over here. And we'll keep on working on this. So this is the new snippet that we're happy with. All right, so obviously, good enough as it is. Okay. So now we have this global location, and we said that global equals some math function here, and turns out that the global location is just is derived from here. So we can now strip this out of here because we actually have the global. Now the other thing is, well, is global defined up here? Yes, it is. Okay. So global pixel location. Right. We might want to say what that's about. Global pixel location. Actually, these are both global pixel locations as index, right? So this is as index, and this is as XY, right? So one is as an index, and one is as a XY. So we want to make sure of that. Pixdex global. Okay. PAINT5D is coming from this function, and these variables are no longer correct, right? Because it's going to be this stuff here. So we can take this and we can leave these in the comments, just so that maybe it'll make it easier for us to find other related code, perhaps. Or I think that maybe the most important thing is actually the examples. I think the examples are going to be more important than the synonyms in terms of looking at the code and trying to find our way around it. So I'm going to do that for a second. Also, I'm going to check my messages really quick on Twitch, because I see 3 people have, like, whispered to me. Okay, cool. So let's write this function. This is the next function we need to write. But before we even write this function, before we even get ahead of ourselves, I think it's time to, like, stub this function into the code base, right? Like, before we start writing even more and more code, I think we just want to make sure that what we have currently compiles, right? So, Texel fetch, whatever, that function already exists, and part of that is going to be inserting this code in the proper location, right? So if we so there's no forward declarations in our GLSL code. I don't even know if GLSL has forward declarations, but we have to make sure that any functions we're referencing, for example, this function, that we include our code after said function, right? So we do not want to forward reference any function. Okay, so this thing here, we'll just say, this is a pixel index. Here, let's just say return, and we just want to get something to compile. And so my C99 compiler is going to yell at me if I do not use any variables. So we have to write something here, and we want something that will compile as both GLSL code and C99 code. So I think my best option here is this, right? So we're just going to stub this in for now as this, right? We're going to just take all the variables, multiply them together, and then multiply them by 0, right? Which is obviously not going to do anything nice. But this is just the bare basics so that we can get this to compile, right? So 0 is a valid index location of a pixel. So we'll still be working with valid data, so none of our asserts are going to catch us. And pixel index, get this global location, Texel fetch that global location using the tau memory in the global thing, and the level of detail is always 0. So that all looks good. That all looks good for a first kind of rough pass. And now let's go into this fragment shader and say, okay, well, where are we going to put that? Well, we know we need this Texel fetch, right? We know that we need the Texel fetch, so it's going to be somewhere, let's go find where the Texel fetch is, right? Let's go find the Texel fetch and say, okay, if this is our Texel fetch command, then we know that the code needs to be inserted somewhere after this Texel fetch, right? Let's kind of read what else we have, though. So we have, like, a bitpack get, and bitpack get, oh, that's just where we were. Okay, so we're gonna open up the code right here. I think we're gonna open up the code right here, and then we're just gonna throw the new stuff we need right into this section, right? So, so new feature. And then let's do, let's keep track of what the date is. So 2021, 0210, and then the video ID is 0131. And I've always been abbreviating it as vidIID, even though it would be nice to make it a little bit shorter. But if I want to look through the code for all of my video timestamps, then I'm going to have to be consistent there. So added on date, video ID, and then time, we can make time shorter, right? We can say the time, T for time. I don't care too much about doing that, but the problem here now is that 34:55. The problem here is we're outside of our limit, so we could, you know what? Let's just call it date, and then we're just going to have to assume that we know that date means added on date, because I don't know what else it would mean, right? So we're just going to say you're going to have to make that assumption as to what that means. So 4, 35, and 23 to keep with the conspiracy. So 23. Okay, so right here at this time, let's explain. We're about to insert code that will give us access to the texture as uniform memory, so that we can flip between different auto tile sets that are being rendered in the PAINT5D system. That is what's going on right here, and we're just going to make this little divider here so that we can see where that new code is delineated, right? We want a sharp delineation here and here for this insertion point. And now we're going to take this code and we're going to just paste it in there, right? So we're just going to take this all and we're going to cut it out of here. We're going to go over to here and we're going to just throw it in there, right? We're going to just throw it in there. And then after we throw it in there, we're going to save this. We're going to save these scratch pads. So the scratch pad has absolutely nothing in it now. And the next thing is, we have to... I'm going to do this. For now, this will be a temporary thing for now. But I just want to make it a little bit more obvious where this delineation is. And let's look it over, make sure we think it's going to compile. Pixtex, global... we'll know fairly soon whether or not it compiles, now that we've thrown this in here. Yeah, let's give this a run, try to compile it, and see what happens. So let's go into our mod folder. So this is our mod folder, and if we open up this .frag thing, it is the code that we're currently working on, but it's been shoved into a string, embedded into the executable, and then saved to disk when the executable ran. So I designed the engine to be easily modifiable. So the mod folder is just a folder where all of the shader code that is stored in the executable gets dumped to this folder. And if you want to edit how the game kind of renders, you can go into these individual shaders and you can edit them. And then, if you ever screw up royally, you can take the file you screwed up royally and delete it. And then when the executable starts up the next time, it'll say, hey, I don't have shader number 1. Let me go read from my source code, find that shader, and then save the shader onto disk, right? So if the shader exists in this list in the mod folder, it'll be read from here. But if we delete it out of the mod folder, it will be read from disk. And this is very important because we're about to reload this shader, right? We've made some changes to the shader source, so we need to delete the cached copy from here. So I am kind of nervous because I feel like if this works the first time, I'll be surprised. I feel like there's probably something I screwed up. I know it's not completely finished yet, but my luck as far as getting things to work the first time, not so good. So I thought ASS was my assert macro. Comparison of unsigned expression is always true. Oh, so that's just... that is a C99 error. So the other thing is I get the benefit of compile time checking of the C99 compiler to check my code. So, so yeah, these are unsigned. Are we going to keep them as unsigned here? Well, let's look at the other code here. Is this using unsigned? There's no reason for it to be negative. We're going to keep it unsigned. Yeah, we're going to keep this unsigned, yeah. So we're going to keep this unsigned. That means we got to just remove this check here. That's fine. I'm thinking, do we need it unsigned or should we keep it signed? Yeah, I'm going to keep it unsigned. Unsigned is, like, specifically these types are actually, 8-bit integers is what we actually need. We actually need 8-bit unsigned integers, but we widened it to 32 bits because we can't be so picky in GLSL code. But in the GLSL code, we can be at least picky about our signedness, so I guess why not keep the signedness the same instead of turning it into an integer? Why not? I think that's fine. Now I don't know if I'll come to regret that later, because maybe I'll run into a whole bunch of, like, casting issues later, and I'll be very annoyed. Int is not what I want to use. Error, expected expression before int. So that means my snippet is not correct, most likely. Let's go look at that for a second. Bracket balancing, yes. So this is, remember, this is compiling both as GLSL code and C99 code, and we can't just call this int. We have to use a macro called makeInt. So let's make sure that we have a macro called makeInt. I know we have some other macros called make whatever. So we don't have a macro called that, but I'm sure we have make something or other. MakeInt32. Oh, it's called makeInt32, of course. Now the question is that an int32 or is it a uint32? So let's go look at that for a second. The global location is a ivec2, so an integer, signed integer. So we want make int32, right? And then we're gonna have to okay, now everything is kind of here. Define T is for trunk. And F is for float, but we can't do that either, right? We have to do make F32, right? Because remember, this has to compile as both this has to compile both as C99 code and as GLSL code. So where we're seeing this F, right? We're using a constructor style cast, which we can do in C99, but we can't. Sorry, we can do the constructor style cast in GLSL, but we cannot do that in C99. So this needs to be make F32, and this needs to be make F32 as well. Okay. And now everything is kind of a mess, right? I did want everything to kind of line up nicely, but I think we're past that part. I would like not to have too much indirection with our macros, so I don't really want a macro that leads to another macro, because I'm worried about the stability of that. Now, that may actually be fine, but I'm a little bit paranoid. I'm going to lean on the side of don't do it. And let's try to, like, make this not look so ugly. Sure, why not? Okay, so make F32. Do we have something for that? Do you have a macro for that yet? Indeed, we do have a macro for that already. Excellent. So now we have to think about, we're going to edit our snippet, though, right? So we want this snippet to work out of the box for the original use case. That's kind of the way I do my snippets. So we're going to take this and, oh, did we change the header on that? Let's paste this. So it seems that we have, that the code, we changed the, here, let's check that. Okay. Okay, now let's go look at this again. Let's close the Scratch file for now. And say, does that look correct? So we make int 32, which will, it'll use a C99 cast if it's C99, and it'll use a constructor style cast if it's GLSL, right? And casting should bind tighter than division, so we should be fine there. D is for the pixel index, T is for trunk. Okay, yeah, so I think that looks good. So let's give that a shot and see if that compiles correctly. And then if that compiles correctly, we'll be one step closer. Implicit declaration of function trunk. Oh, yes, if we're going to do that, we need a macro for that as well. Okay, so once again, trunk is not something that exists in C99 code, so we're going to have to make a polyfill for that, right? So I'm just going to call it, where we're using trunk here, I'm going to call it TRU for trunk, which could be kind of confusing because it's like, you know, it reads as true, but I want to keep most of my macros to like 3 letters, so I'm going to do that. Now everything is getting a little bit big here, so we're going to remove the T here, and we're just going to say, you know what, so index to xy. So define G. Okay, so this is global xy. Right, so one's a global x. This is a global xy. This is a global dex index, right? D and G, and then over here we can just call this G over here. So we can go G, and this where this is glow, we can call that G, and that saves us just enough space where we're not exceeding our limit, right? In fact, we could probably go add a little space there, like that. And we could also kind of, if we wanted to. Okay. So we're going to have to go create a macro for this truncation, right? So let's go up to where we're creating all these where we create these macros and just say, we have this error macro. Let's just kind of shove it in the end of the list, right? So let's go define true for trunk, and this is GLSL code, right? So if it's GLSL code, it's just going to be called trunk, right? So 1, 2, trunk, and 21, right? Okay, and if it's down here, we're going to define TRU as AAC 2020 poly OGL trunk, right? We can just call it poly OGL trunk for a truncation, or we could call it a truncate. Maybe we want to call it truncate, I don't know. Or maybe we want to name it just the same as this. Maybe that would make more sense. I tend to like shorter rather than longer, so right. Okay, so now we have to add that polyfill into the code base, right? So the truncation function right now is working with, I think it's working with integers, right? It's working with no, it's working with floats, and it's giving back an integer, right? Let's go look at that for a second. So first of all, let's go open up the poly-OGL system. And we have the poly-OGL functions here. Let's put this over on this side. And let's go look for where we're using this. Decide what this needs to be. Truncate float 32 divided by float 32, and then make int 32. Okay, so the truncation, as it is written here, takes a float, returns a float. And I'm fairly certain that is the correct behavior in GLSL code. So let's go get that working, right? Let's go add this trunc function somewhere. We have this thing that says do not paste into GLSL code, and that is great because that is true. Let's just throw it into here. Let's just throw it into the section. So let's keep up with it looks like everything we've called GLSL polyfill for some reason. Like everything has been marked with GLSL polyfill, GLSL polyfill. Let's just keep with that convention, right? So we have a lot of inconsistencies as to how we do things in the code, but on a file-by-file basis, we should at least keep the same consistency, right? So GLSL polyfill truncate. Trunk. I guess maybe we should name it how it's called in GLSL code. So okay, and we know that we have to take a, let's indent this and say float 32, and let's go look for what we called that in here. So this is the name of it. Now the case might screw us up, but I like camel case for function names, so technically camel case for trunk would be a capital T. So trunk, and then we want a float 32, I don't know, how about calling it float 32 in, and then float 32 f32 out equals f32 out. Here's what we're gonna do. So we can just do this. So I32 out equals a cast, int32 cast of f32 in. Right, so if we cast it, it should just truncate. If we cast it, it's just going to, the default behavior in C99 code, as far as I'm aware, is to truncate. If we cast, we can make sure that does cast to integer truncate in C99. Let's make absolutely sure that this is the correct behavior. So when we cast to an integer, are we going to truncate? Casting to int will truncate towards 0. Floor will truncate towards negative infinite. Oh, got ya. So when we're dealing with things that are, if you have the possibility of a negative, you want to be careful. There's a differentiation between floor and truncate when we are dealing with negatives. However, we're dealing with pixel indexes and pixel XY coordinates, and those are always positive, so we don't have to worry about the distinction between floor and truncate. Is there any difference between this and this, right? Yeah, so, okay. Stack Overflow is already confirming what I assumed, so I'm not going to read too much into that. Like, you know, that was just a sanity check to make sure I'm not being completely stupid, right? So we're going to take the float32 input, cast it to int32 to get the i32 output, and then we're just going to cast it back, right? So f32 out equals a float32 cast of i32 out. So i32 out. And did we screw up our bracket balancing? No, we're good here. So let's follow the data here, make sure this is correct. So here's our input, which is turned into this output, and then that output is turned into this output, and then we return that, right? So return f32 out. So yes, a little bit verbose for writing just a simple floor. But if you haven't already noticed, I'm pretty verbose in the way I write my code, right? So, float32 output, int32 output. We can make a note of what these kind of stand for. That looks good to me. I think I'm happy with that. Okay, so now that we have a proper truncation function and our polyfill is correct, so when we are compiling as C99 code, TRU for truncate is going to be this polyfill. Otherwise, TRU is going to be the actual built-in truncate function for GLSL. Okay, cool. So we got that. Let's go back here to this code here and say, hey, is this correct now? Now this just looks very cryptic, right? Where it's like, it looks crazy. Should I really use it as a snippet? And I'm going to say, yep, I'm still going to use that as a snippet. Because I think it still helps. Even though there's a lot of different things that may need to be replaced depending on where I'm using this snippet, it's still valuable to have it in a way where the first place where I ever use this snippet, it needs to be the same, just to give me a sanity that the snippet is correct, if that makes sense, right? So the first time I ever use the snippet somewhere, it needs to reflect exactly how it is in the production code, just to give me sanity of mind that this snippet is correct, right? Because it's not like you can really do any compile time. I mean, you could probably make some type of compile time checking system on this, but for now, we're just gonna we're gonna hackishly make sure that this snippet is correct by, you know, running the code and making sure it compiles, right? So with that, I think we're ready, right? So we got this original formula. We might want to think about this formula for a second and think about if it's correct. So we have the original pixel index, and we divide by 512, right? So dividing by 512 will give us the number of full rows. So the number of full rows would be the y location, right? And we have to truncate. We have to truncate because we can't have floating point, right? And indeed, that is our y value. Okay, cool. So we're good here. As far as I'm concerned, this snippet is correct for the y-axis. Okay, so now we take the y-axis, and we want to figure out how many pixels have we already used up, or how many indexes have we already used up. So we take the y times the stride, which is also the width, and that tells us how many pixels have already been used up. And then we take d, which is the pixel index, and we subtract how many pixels have already been used up, and that gives us a remainder, and that remainder is the x, right? So that's just how index to xy formulas work. I'm not going to explain it any more than that, just because it makes sense to me, and explaining it in any more detail, I don't know if I could. I don't think I could without spending a lot of time on it, so so that looks good. That looks good. I think it's time to just give it a shot, try to compile this, and see if we got things working, or if I've made some type of stupid syntax mistake somewhere. Okay, so it's compiling. That's good. So that doesn't mean that our shader won't. So okay, our shader has not been instantiated yet. That's good. Okay. And now if we look over here, there's a shader 1. Let's see what happens. Okay, syntax error. So somewhere we made a syntax error. I was hoping not to have this happen. But it's happened to us. So we got to look at this, and now we got to look in here. And this is implicit cast from a uint to int. Okay, got it. So this is kind of why I was like, we've written too much code. We got to make sure it still works. Because even though what we've done was like really trivial code, we've already made a stupid mistake. So we got to figure out what in here is doing an implicit cast from a uint to an int, right? So the first thought is this right here takes u32s for some reason. And this is taking ints here. Okay, you know what? So now that I think of it, defines by default. Like when we have just a number here, by default this number is going to be an integer. By default that number is going to be integer. Now, even though originally I coded this with like an unsigned 8-bit integer, if we want to just avoid headaches, the locations should just be defined with signed integers. That's just going to avoid headaches, because right here we're mixing a uint with an int, so that's giving us problems. Now we do need, this is int32 here. Okay, sure. So we're going to change this to int32. So a lot of the signatures of this are going to be like whatever is going to be easiest to work with in the GLSL code. So we're going to change this signature to use int32. And then when we're calling this, we see that, oh, this stuff is, okay, we're going to have to change this also to an int32. And I don't think we're using this anywhere yet, are we? No, we're not using it anywhere yet. But yeah, so I think this is going to make the most sense, because eventually the values that we're going to call with this, right, with we have to use this value, and this value, they're going to have to somehow be injected into the shader as like defines. And it's going to be a lot easier if those defines are integers, right, can just be encoded as a literal 0, 1, 2, or 3, than if those defines are unsigned and then have to be wrapped in a uint cast. So it's just going to make our life a lot easier if these are signed integers. Now we do have to, right, it says get u32, so this has to be a u32 here. U32 var, texel fetch, that looks good. Okay, so let's give this another shot. We're going to have to delete this shader out of here now. So, shader number 1. And we're going to give it a run, and we're going to see, if we have fixed that syntax error, or if we haven't, right? So the idea is that we have to write a little bit of code, run it, because if we don't... Okay, so now the code's running. So the code we've added so far still works. Or is compiling correctly, so that's a good sign. So we know that all this scratch code we've written so far is working, right? I was actually... How does that work, though? Oh, yeah, okay, that's right. Yeah, so if we... Yeah, so this is good for here. So now the next thing is... So the next thing is this function here, right? We need to write this function, and it's based on... Let's close this polyfill. We don't need this polyfill anymore. Now, this function here, right? We wrote it in a way to where we could just take this, and we could find it in the original code, right? So if we look in here, we can find the original function... and figure out how these calculations are done. So it looks like this is the template to write the GLSL equivalent. This code reads plus writes on the CPU side. We need a version of this to transcribe to GLSL, read only from the GPU side. Okay, cool. So, excellent, because now we're at this part, and this comment says exactly what we think it should, right? So, we'll make a little update here, right? So, we'll say, you know, update at vid IID 0131, and the time is 5 hours, 4 minutes, 42 seconds, because we want to be cool. That function is, right? So we just want to make an update, right? So the update for this commentary is that the function we're talking about, the GLSL version of the function we're talking about, is this function, right? So we're about to, so this function actually only exists so that we can write the GLSL version of it, which is kind of like hacky, but that's the way it is right now. So, so if we transcribe this carefully enough, we'll just be in a good position here. If we don't transcribe it correctly enough, then we're gonna end up in some trouble. So we might want to be like, go over here for a second to do unit test this function, right? So we need to unit test this function eventually. Now, if we carefully transcribe it, you know, it'll probably work, but we should still write a unit test for it. Okay. So, okay, so we have to use indexed xy calculations multiple times to get tx, sx, vx, etc. Some asserts to check our math. Then we have to get the final px, py by multiplying the different memory segments. And then some asserts. Not too bad, not too bad, not too bad for the calculation. So, let's transcribe this code into the GLSL equivalent to get this working. So, the first thing is we've looked at this carefully, right? We've looked at this block of code carefully, and we're fairly certain that this indexed xy calculation is correct. And we're going to need it, and we're going to need to use it 3 different times right here. So, we're gonna hope that we're absolutely sure that this formula is indeed correct. And there's no need to, well, if we look here, these are different indexes, so we're going to have to, okay, we're going to get rid of the glow for global here, because we're not going to use that in the 3 copies we have. Now, D for dex. Dex is a fairly big index variable. Well, you know, let's just let's go through here and so tx and ty, right? So tx and ty. Okay, now this D for dex is actually this index here, which corresponds to, it's called dex tau, so it corresponds to this index. So I would like to just kind of throw it in here, but, right, this is already quite verbose, right? So we're already running out of room, so we're just going to throw it in there, right? And now the next thing is, right, we see these 4s, right? So it's on a conceptual 4x4 tile map, if that makes sense. So we need to make sure that these are 4s. Okay. And if we did that correctly, right, so this is this supposed to be, oh, did I already screw that up? Oh, I didn't screw this up. So, this is a different formula, right? So, this is a formula that uses modulus, and so we get x and then we get y. But the formula that uses truncation has to flip it around. So I do see why I prefer this formula, because, you know, I like to consistently write my code, right? So x's and then y's, right? X, then y. So this formula is kind of very awkward, where it's like you have to figure out y before you figure out x. So I do not prefer this type of formula. However, it's GLSL code, and we don't have this modulo operator. So we have to write it in a GLSL friendly way. So we got the 4s. The 4s is the same, but the y's are diagonal, right? We derive y, then we use the y to get x. Makes sense. Okay, cool. So we could make a little note here, right? So we could say index xy GLSL, And then we could tag each one of these sections, maybe. Here, no, let's not take up any more space here. Let's just tag it right here, right? How about we do this? How about we tag it like this? So I just I want little kind of like breadcrumbs to tell me like where the code came from, if that makes sense. So now we just gotta duplicate this. 2 more bash scripts. Okay, we gotta duplicate this 2 more times. And we have to replace tx. So the next one is s. So instead of t's, we have s's. And the next one down here is v's. So v's, v is for variable, by the way. So it's t is for tau, s is for sub, and v is for variable. And they're the abbreviations for the different memory subsections that I'm using. Okay, so now we need 4, 4, and 16. So this number right here is going to need to be a 16. Okay, and then we want to say, hey, let's take these variables and kind of like paste them there. Let's take this variable here, paste that there, so we know kind of where this code came from. And it looks like we also have like a diagram to tell us like more about where this stuff comes from. So it says C diagram var cell. So C diagram var cell in, what's the file though? Is it taudepot.data? I'm gonna guess it's in taudepot data. So let's look at taudepot data and see if there is a diagram for this. So this looks definitely, yeah, dia tau cell, dia var cell, and all that stuff. Yeah, that's in here. Dia var cell right here. Okay, so now that I realize that, dex tau, dex sub, and dex var, let's put those there. And now let's, how do we want to note this? Do we want to just throw this together in a big crazy block like that? I don't know if I like that. I think that is a little bit too chaotic for me. I think that I think that extra visual space is kind of nice. And we're actually going to keep, I thought about it. So we can just do lib/taudepot. We don't need all the extra file path. So this is dia subcell, or actually, that's not the right diagram. Dia subcell, and then at the very top, this is dia tau cell, right? Dia tau cell. And then this next thing down here, so dia subcell, dia tau cell, and then the last one here is var cell. So dia var cell. I can just do this. I know that's correct, right? So these are the dia for diagram hashtag. So hashtags means it's an off-boarded comment, right? So obviously to put this huge diagram right above this code would bloat our code a lot, right? It would make the code almost impossible to follow because it would be so bloated by commentary that we just have a hard time finding our way around the code. So a lot of times if we need some type of commentary, we will export our commentary somewhere else, right? So hashtag means that the commentary has been exported somewhere else. Okay, and then, but yeah, tau cell. So the next thing is we just want to make sure that, okay, we're going to look at this diagram here, and we're going to make sure that everything kind of matches, right? So we could do these 3 colors here, and then we could do the same three colors here, right? Okay, so that looks good. Okay, and then the 4s and 16s, so let's go, okay, so here's 4s and here's 16s. And there's also, you know, 4s and 16s here. How about, what else needs to match? There needs to be ty and tx, and that's not going to be in the same positional location. sx, sy, vy, vx, right, because there's tx, ty, and this doesn't match exactly, right, because the formulas are slightly different. But the idea is to take an index and convert it to an XY location. So now these indexes need to be correct. So right here, dex tau, dex sub, and dex var, and that looks quite correct. Another cross check I might want to do is it's D for dex, right? So or no, it's T for tau, right? So we could go T, S, and V really quick and see if that like lights up correctly. And it looks like everything looks correct there. When we're spot checking, we can see these colors here, and these colors here. We got these 3 columns of color. So yeah, cross-checking it really quick, I'd say that the formula is correct, or the formulas are correct. And so now we're just gonna box it up a little bit and declare the variables at the top of the function, right? So. So let's okay. So now we need quite a lot of variables here. So what we could do is we could steal this from here, right? We can steal this from here, copy it, and then we can open this up, give it some room, paste it in there. And so we know that since we cut and pasted, we know that these are exactly the variables that we want, right? Now because of that, we could take the commentary here where we're saying see this, see that, and we could just say, we could put that commentary here. So this is dex tau's XY location, right? So this is dex tau's XY location, right? So this dex tau here. Then same thing for each one of them, right? So kind of repetitive. So let's so dex tau, this is dex sub, and this is dex var, right? Dex var. Tau, sub, and var. T, S, V, we got X's, 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 we got Y's, 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 right? So if we look at this, all the coloring should look consistent, so we just need to visually lint the code to make absolutely sure that it is correct. So I'd say, yeah, that looks like the correct first part of the formula. So now we have some asserts here. 512 divided by 4 is 128. Check our math, right? So do I want to check our math? I get why we're doing this. We're just checking some assumptions on some math here. I don't know if this check is going to really help us. It helped us make the original function, but I don't really think it's going to help us as far as transcribing, right? Because these are all hard-coded values, right? Now, if they were asserts that were checking calculations involving variables, then yes, I would be, I think it would be useful. But here, I don't think so. Okay, so global pixel XY on 512 by 512, right? So we need this, so let's steal this, copy it, and one thing we're immediately going to change is this declaration and assignment at the same time. Now, it might be okay, but I don't want to risk it, right? Like, I want to write this code as simple as possible because it needs to compile both as GLSL code and C99 code. So the simpler we write our code, the less problems we're going to have. So, global pixel XY on whatever, right? So we could actually just say pixel X global on 512. So that's pixel X, and this is pixel Y, right? PX, PY. So here's PX, here's PY. Let's get rid of the type declaration at the front. Okay, so we got these calculations here. We got to make sure this is integer math. So let's look at this. Make F32, int32's here. Int32's are being inputted, so we're not mixing unsigned and signed anywhere. That should work. So these are X's, these are Y's. It was cut and pasted, so I'm not too concerned that it would be wrong. 512 divided by 4, because, why is it divided by 4? Let's go look at the diagram. Why is it divided by 4? Oh, 1, 2, 3, 4. Yeah, because 4 slices on each axis. Because I thought 4, I'm like, there's more than 4 cells. There's 16 cells, but sliced 4 on this axis, 4 on this axis, gets the 16 cells. Okay, I see what's going on there. Okay, yeah, so that's fine. Okay, so that formula looks good. And we're going to need to go 1, 2, 3, 4, and 1, 2, 3, 4. That does mean some of this commentary is going to need to be condensed or removed, even though I really do like this commentary, right? So we could, well, let's see what lines are kind of offending here. So what lines are kind of like going past the column limit, what lines need to actually be shortened, and what lines are good as is. And so that way we can kind of assess the problem here a little bit more and figure out how much work do we really have. If we really want to take this and get it to this new column limit, what do we have to fix? So let's just call it pix per var, right? Pix per var. And then okay, let's change it to pix per var. So 4 pix per var, right? So that's kind of ugly. It's kind of ugly, but it makes it fit. So also in my shortcuts, I might want to make note of like what the heck that means, right? That's very terse. So pix per var, or pix per var, or pix per var. Anytime I type pix per var, pixels per variable. Right? So just make a note of what the heck that means, because that's very cryptic. Okay. Okay, so that looks good. We've kind of shaved off a little bit of the column limit so that we can work with this code a little bit better when we're processing it. So assert that px modulus 2. We are trying to return a 2x2 cluster of pixels sliced out from the texture. Thus, the upper left corner should always be evenly divisible by 2 on both axes, right? That is valid. However, as I had said before, even though we are going to use an assert macro over here, because we can't assert in GLSL code, the way the preprocessor works in GLSL seems to be that it will evaluate the statement before it removes the statement, and therefore that assert, having a modulus operator in it, is going to actually take a decent amount of work to transcribe over to here. So we're not going to put it in this code, or, yeah, we're not going to put it in this code because I just don't want to deal with it. Okay, xy to index formula for top left pixel of our 2x2 cluster of pixels representing a single variable. Got it. So I know exactly what that means. So let's steal this. And there is pixdex. Now, we're going to have to change the indentation a little bit here. So it looks like we could kind of indent that like that. And then indent like that. And I'm good with that. So this kind of dummy calculation, we can get rid of the dummy calculation because now we have the actual calculation we care about. And what else? So pixdex needs to be declared, right? So So int32 pixdex, right? And this is the output variable. Output slash return variable. So this is the output slash return variable right here. So bam, right there, bam. So pixdex and yeah, I mean that looks good to me. Oh wait, hold on, I scrolled too far. Pixdex. Okay, so now the next part is, can we get this to compile? Does it still compile, or have we done something stupid again? Right. So first thing we want to do is we want to go into the mod folder. We got to delete this, and after we've deleted this, we can recompile and hope everything works. So let's give that a shot. That's not compiling, because I'm lazy. Ah, wait, there you are. There is my build script. Okay, so let's give this a run, see what happens. Let me check my whispers while we're compiling. Okay. Okay, so let's give this a run, see if the shader compiles, right? We're only just trying to see, hey, does the shader compile or does it hate me, right? So looks like the shader is still compiling. Cool. So we're going to assume that we've carefully enough edited this that, you know, we'll find out pretty soon if we're wrong here. So the next thing is that we want to use this to get the hard-coded offset value, right? So let's go over to find where we put AUS DEX, right? AUS DEX was somewhere in here. It's in quite a lot of places, actually. So this is the AUS DEX we care about. And right now it's hard-coded to 14, right? So we're going to unhard-code this right now. We still need to finish the function, but we're going to unhard-code it, right? So int32 AUS DEX, and then AUS DEX equals, and we have to fetch, the hard part here. So we could hard-code this right now. We could look at our source code and correctly hard-code this. So we still have some hard coding that we're going to have to get rid of. Okay, so there's still some hard coding we're going to have to get rid of, because we're going to put it in here. But we can look at the source code and figure out what values we need to hard code just to get things working, you know? And then once it's working, we can unhard code it. So this is going to be a bit of a challenge. I'm hoping this will work. I've done this before in my JavaScript version of the code base that I wrote many months ago. I am kind of scared that I'm going to screw this up. Let's see. So tau depot. So the first thing is we're going to use tau 15. So what is it? Tau sub and var, right? So tau is 15 here. So 15 is the tau. And then the sub, the subsystem should be PAINT5D, I believe. Or are we having it, or is it in PAINT5, or is it in Tau Depot? So that's also kind of confusing that I have a Tau Depot section and a PAINT5D section. Well, these are variables specifically for the PAINT5D editor, therefore they should be in PAINT5D, right? PAINT5D this, PAINT5D that. I don't think I have any variables that are specific to just Tau Depot, which is kind of weird, right? But Tau Depot sub PAINT5D, is that declared in here? Oh yeah, so it's 1, right? Which is a sensible number. Okay, so we have that. And then the next thing is, we have a series of variables. So this offset DEX is this variable right here, whatever the heck this is, wherever that's declared. So offset DEX is encoded as 8 right now, right? So we can take all this and we can just hard code it right now, right? So, so this is tau, this is sub, and this is var. So the var is yeah. So we'll right, this is the var that we want to use. The sub is PAINT5D, right? So the subsystem is PAINT5D. The tau is tau 015, right? And if we hard code all of this, it should actually work. The keyboard binding should actually work. But then we need to get rid of this ugly hard coding, right? We need to somehow inject these defines into the code in a way that will work both as C99 code and as GLSL code. So we'll have to think about that. But first, let's give that a shot and see if we can actually get some keyboard responsiveness. Now, the thing is if we're going to get this to work, because the current tile set we used is the same for all layers, we're not going to have anything, we're not going to see anything, right? So in order to fix that, we should go into the PAINT5D system here. So PAINT5D functions, and we should look for the P5D pattern key. And the P5D pattern key right now is using this nice little tile set. We should use our this data set to get this working. So let's give that a run, because I think this will start to get very interesting very quickly. Are we missing anything? Okay, we got this thing hard-coded here. This diagram we don't need to have open anymore. This is hard-coded. We have to fix that hard-coding, but first we just want to make sure we can compile, right? So let's look over here. This first shader, we already deleted it. We just deleted it, so that's good. And so now let's just clear this, and let's give this a run. Let's give this a run and see if we can get this compiling, right? Okay, moment of truth. I don't think anything should have broke. Okay, so P for pattern, right? Okay, so now I don't remember what keys actually do this. So, let's close this. You know, that's probably one of the things I should have looked at. So we can find that really quickly. Let's look at our keyboard bindings. So let's go over here really quick and open up keybind and be like, what key did I use for that? Because I don't remember what key I used for this. So keybind.data, and let's look for AD maybe, or actually it's going to be like offset next and offset back, probably AN next offset, yeah. So P5D AN and P5D AS. So if we look at this, okay, so Y and N. And that is, yeah, Y and N. Okay, Y and N, got it. So Y and N are the letters I want to use. Okay, so let's go back in here and see if this works. See if we can. It'll be very obvious. I already tested this data set on different autotile set indexes. I had to, manually change the number in the shader, but I already know what I'm to expect if this works. So. Let's give it a shot and hope that it works. So, P for pattern, and now let's do Y and N. So, Y and N, no dice. So that number is not changing in the shader code, so that sucks. So, let's go all the way up for a second, and then see if maybe... Okay, so we got this creepy little face thing. We're gonna go all the way down. So we're gonna go... I'm just gonna see if maybe the key works. Okay, so we're at 0. Okay, 1. Nope. Okay. I'm gonna mess around still again. So, Y. I'm gonna go all the way up. I'm just gonna see if this is actually changing things, or if indeed we're not really getting anywhere here. Okay, so we're not really getting anywhere here. So, if I remember correctly, we may not be texture pushing this yet. Yeah, we're not pushing this texture up to the, what do you call it? We're not pushing the texture that stores this information up to the GPU yet. Because I remember I had a to-do to be like, hey, don't forget to do this to-do somewhere. And the reason why I haven't done this yet is because I know the only texture push I'm doing in the codebase right now is a full texture push, and this will require a sub-texture push. And I have not done that yet. So I need to do that. I need to add that code. So let's go into our agenda, which is getting kind of long, but let's go into the agenda screen here. So we're gonna forget about gent up, because I think it's gonna be a time sink to try to create code that's gonna auto-generate graphics. So I'm gonna change my to-do list here really quick. So this is my to-do list, and this thing that was 17, we're going to consider that done. We're going to make a new 18. Sub-texture push of tau memory. Location where I need to do this should already be stubbed in. Okay, maybe that's a little bit too much, but yes, the location where this needs to be done should already be kind of stubbed in. So we're just gonna renumber these. So 18, 19, 20, 21, 22, 23, 24. Okay. So I'm gonna take that. I'm gonna go back to my agenda screen, and I'm gonna paste this into the agenda screen. Okay, that looks good. And I'm going to move some things around. Yeah, so that's the next thing I need to do. So before we can get these keyboard bindings to work, and these keyboard bindings and all that stuff is really important, right? Because if we can't get this working, then there's no hope for Josh to be able to use the editor, right? So keyboard bindings, being able to get input into the game is kind of an important thing, right? So we're going to... I'd say, let's see how many push-ups I have done right now. So I've only done 40. I need to get to 130 for the day. So I think I'm going to stop the stream now. And, so I have entertained the people who randomly showed up. And most of everyone has kind of disappeared, and I've been going for a while. And I didn't really expect to even get this much time done today, because... I coded for 20 hours, Monday through Tuesday. So I wasn't expecting to be very productive today, so I'm actually surprised. So I'm gonna do, I guess, maybe 40 more push-ups, jump on the trampoline, give my girlfriend attention, that kind of stuff. And then maybe I'll come back and do this, later. So, let's see. At the, I don't know, screen. So really what we've been on is 62, 63, but really it's not this anymore. What we've not been doing this, we've been doing, right? This is the task, if you will. We're just trying to get the offset DEX into the shader. So as a little summary of what's going on, that's what's going on. This has been video 131, and the day is Wednesday. Is the day Wednesday? Yes, today is indeed Wednesday. Excellent. So yeah, I'm gonna go get out of here, do my push-ups, do some of my push-ups, do like 40 more push-ups, and then I don't know what'll happen from there, but we'll see.